Okay, dear colleagues, hello. I would like to express my deep gratitude for your acceptance of the invitation to participate in today's defense. I fully understand how difficult it is now to organize and participate in such an event through the internet. And we had this example today. This pandemic has created great problems for all of us. Now, in accordance with the regulation rules of the University of São Paulo, we need to establish the sequence of speeches by the members of our commissions. And in accordance with the rule, the president of commission must suggest some order. And my suggestions will as follows: that first speech, my proposal, it could be done by Professor Ranajit Ghose from Technical University of Delft. And second one, Professor Georgi Mitrofanov from Institute of Petroleum Geology and Geophysics, Russian Academy of Science from Novosibirsk. Third, Professor Jörg Schleifer from Campinas, Unicamp. Next, Professor Renato Prado from University of São Paulo. And finally, it's my time by Professor Viatcheslav Priimenko from North Fluminense State University. And what do you think about of this priority?
Right.
If there's some objection or another order, please, could you give me such kind of information?
It's okay. Thank you.
It's okay?
Yes.
Yeah.
It's fine.
Fine?
Yes, I agree.
Yes.
Okay. We have no objections, then we can get to work. So, according to the regulation of postgraduate courses of University of São Paulo, the candidate has up to 60 minutes for his speech. And then the members of the commission generally have up to 5 hours, including the candidate's answer to possible questions. More or less this time. It's up to 6 hours in general for all members of our committee. Okay, if there are no objections and comments on the regulation, then we can start our work. We can proceed. Can we proceed?
Yes, please.
Yes.
Yes.
Okay. Okay.
Yes.
Now, Professor Renato, please, could you help me if it's necessary, if it's will be necessary, please, because you are from USP and you know the rule of USP much better than me.
Okay, Professor Priimenko. It's okay.
It's
if
okay.
necessary, I thank you.
Okay, thank you again for members of our committee to accept our invitation. And now I would like give word to candidate Nelson Zuniga. So Nelson, please, you have up to 60 minutes for your presentation.
Just let me enlighten. Well, I think it's better now. Okay. Well.
Okay.
Nossa, já colheu. Acho que não muda. Pronto, assim já. Ok. Can everybody see the screen?
Yes, yes, yes.
Okay.
Yes.
So
Yes, it's okay.
Yeah. Okay.
Well, at first, good evening. Actually, good evening for Professor Mitrofanov. Good afternoon for Professor Ranajit Ghose, and good morning for the other members of the committee. My name is Nelson Zuniga. This is my PhD thesis defense. It's entitled Non-Hyperbolic Multiparametric Travel Time Approximation for Converted Wave and OBN Data. My advisor is Professor Viatcheslav Priimenko, and my co-advisor, Professor Fernando Ribeiro. And my thesis is focused in develop many techniques and methods to increase the quality of the accuracy and the processing time for the velocity analysis during the step of velocity analysis in a seismic processing. Well, I'll talk about few important topics that we're talking about today. So I'm using the multi-component seismic because it presents a more complete wave field, because we have information of P wave and also information of S wave. However, for offshore exploration, we need to use the OBN technology to perform the acquisition of the S wave. So I will show you later how it works. The models we're working here today are from Prado, from Santos-Basin, and the central proposal here is about an automated peak, an automated travel time peak, and the phase analysis to perform to obtain the information of the target reflection, and this reflection is the reflection from the interface between the bottom of the salt structure and the top of the reservoir. We'll talk about non-hyperbolicity and non-hyperbolic equations, because after obtaining the information of the reflection event, we must calculate with several equations and make a comparison among them, and with this we can determine which one is the best option to work for this kind of model. We also performed a topological analysis because it's important to determine many characteristics of these equations, so we can determine which one is the best for different kinds of problems, and also we can say if what kind of optimization algorithm should be used for this kind of problem. It helps also to use the variation of norms. So we have the L2 norm, the least squares, and the L1 norm, the least absolute deviation. So this is important to analyze how the topology of the function, of the objective function, should vary with each kind of norm. So the main objective here is to develop a generalization of an approximation which is able to consider the non-hyperbolicity related to the vertical heterogeneity, wave conversion, and difference of data between source and receiver. Because the other equations are not able to consider all these conditions together. But it's important to mention that it's not necessary to recover the information about how each phenomenon influences the non-hyperbolicity. And the main focus here is to determine how strong is the non-hyperbolicity and to control it to obtain a better velocity information. The other important objective is to study the complexity of the objective functions, aiming to understand the topology concerning its unicity. Well, if the equation is unimodal or multimodal, because it's essential to know which kind of optimization algorithm we should use to be able not also to determine which kind of optimization algorithm, but it's important to be able to select the best combination of which kind of equation and which kind of optimization algorithm. It's important also to compare the proposed generalization to the others to determine which one presents also the best processing time, not only the accuracy. And I think the essential proposition here, because it's how it starts to obtain all of these informations concerning the three first objectives. This one is essential to develop the other three. So to propose an automated travel time picking technique able to obtain the target reflection. We'll see that there is some limitations concerning this method. So we need to understand which kind of constraints we should use to determine which kind of model we can work with this kind of automated picking. And then to propose a technique able to identify the critical angle without velocity information, because it's also interesting. It's not directly applied for the main structure of the thesis, but it was very interesting to understand how it works, and it helped to develop this kind of technique, the travel time picking. Well, so why we're using multi-component seismic? The central event we're using here is the conventional event, where we have an incident P wave and a reflected P wave, and an incident P wave and a converted and reflected S vertical wave. We're not working with horizontal waves, and we cannot use the incident S wave because we're working with offshore models. So the S wave does not travel through Newtonian fluids like water, so it's not possible to obtain with this kind of event. So the ratio between the P wave velocity and the S wave velocity allow us to perform a better geological characterization. So this is one of the most important characteristics of using the multi-component seismic. So another important information we can obtain with the multi-component seismic is because we can get the seismic sessions even with low P wave reflectivity, because they have the information of S waves, of course. And then we have the increase of the resolution once we have more information, a more complete wave field. And with all of this information, we can obtain a better imaging of high angle faults and imaging through gas clouds. Well, however, the wave conversion generates a non-hyperbolicity. So in a single layer model, a simple single layer model with where you have a conventional reflection, we have an event that can be described as a hyperbola, like this. However, even in a simple model, when we have a wave conversion, we have a difference of velocity between the P wave and the S wave, so we have a difference of angle, and then we have this difference of between the events. So at the beginning, the event is still hyperbolic. However, it starts to get non-hyperbolic. Another kind of asymmetry is concerning the OBN technology to obtain the S waves. So when we have the source on the ocean surface, and then the receivers in the ocean at the ocean bottom. So with this kind of organization of acquisition, we have the possibility of obtaining the S waves. However, we have this asymmetry concerning the difference of distance between the incident ray trace and the emergent, the reflected ray trace. And it also generates a non-hyperbolic event. And finally, we have the RMS velocity, because in multi-layered media, you can see the ray paths are, with the baud lines, they're more complex because they characterize they depend on the refraction due to the difference of physical properties among the layers. However, the RMS velocity is the square mean of the velocities above the reflection. So this is much more simple, because as you can see, the dashed line. And once we have this for short offsets, we have a small difference. So it could be considered hyperbolic. However, for longer offsets, we have this difference. We have an increase of this difference. So this discrepancy generates a non-hyperbolicity, as we can see here. So with the combination of three phenomena, we have extremely strong non-hyperbolicity. So it's a very unconventional problem. So it could not be treated as a conventional seismic, considering only P waves, or considering to use only the hyperbole equation. Well, so for starting from the beginning of the combination of techniques, I proposed the automated travel time picking with a PVO analysis, phase versus offset, phase variation with offset. And then this PVO analysis proposed here is a technique which is able to perform the inversion of the frequency spectrum for each trace, with the objective to record information on amplitude, frequency, and also phase, using the spectral recomposition approach. So we have this mathematical definition proposed by Tommaso in 2010. and it can describe the amplitude. You can find the amplitude, the peak frequency, and the vector of the frequencies is not an unknown here, and we can describe the phase here. So with all this information, we can determine which kind of spectrum we're dealing with. So we can describe if it is a noise, if this wavelet is related to noise, to random noise, essentially, or to the signal, the target signal concerning the reflection we're looking for. So we calculate this with this mathematical definition, and we compare to the observed spectrum with the observed wavelet for each wavelet in a seismic trace. So with this kind of information, we can obtain the frequency, the amplitude, and the phase for each wavelet. So for all wavelets related to noise, and for the wavelet related to the signal we are trying to obtain. Well, so to obtain this kind of information, we start in the first trace. So we calculate the spectrum, and then it fits to all observed spectra of the frequencies, and then we automatically recover and the wave parameters, and then they are compared among them to determine which set of informations are related to noise and which are related to the signal, because in a seismic trace we have much more noise than signals. So we can compare each wavelet related to noise among each other, and then we can determine the discrepancy between them and the target reflection. So after recovering the wave parameters, it's possible to determine if the wave parameters of the spectrum are related to the random noise or signal of the reflection. But it's important, as I already said, but it's important to determine that there's not only one reflection, of course. So we can also mute many parts of the seismogram, aiming to obtain the target reflection more easily and faster also. Well, however, this is only for the first trace. Then we need to perform this to the following traces. But for this, we need to consider few constraints. For this kind of problem, we can consider these three constraints, and as I tried here, it worked very well. So considering the arrival time of a trace always higher than the previous one. So this first constraint is just to make the algorithm calculate less wavelets than it needs. So we're considering the arrival time always higher than the previous one. We can disregard all of the travel times above it. So it simplifies the application of the algorithm. So we can make not only a more accurate recovering of the information, but also reduce the processing time. The second is to compare the difference between the arrival time of the analyzed trace and the arrival time of the previous trace. So we can compare the neighbor traces and to refit to refine the position of the arrival time, comparing to the following trace and the previous one. And the third constraint is comparing and cross-correlating the recovered parameters. So the frequency, the amplitude, and the phase. Because comparing them, we have the the random noise is very similar among the other random noise. So being compared, we can determine, well, all of these are random noise because they are very similar. They present the same kind of frequency, the same kind of spectrum, the same kind of phase, amplitude, and then we can analyze this discrepancy to the signal, to the wave parameters of the signal. So we can separate them and identify which spectrum is related to the target reflection. Well, the models used here are 5 of them from Santos Bazin, from the Pre-Salt, from Santos Bazin, and we tested the automated peak for all of them, and then we used 3 near-surface models tested for phase shift with 2 different kinds of wavelet. So just to illustrate here, so we have the surface with the air gun, the seismic source. Then we have more than 2 kilometers of water layer, and then we have the ocean bottom with the receivers copied here. Then we have the structure, the geological structure. Here we can see the salt structure, more than 2 kilometers, and here the top of the reservoir, the carbonate reservoir. And here we can see the ray tracing, the complexity of the ray tracing for this kind of event, for this kind of model. We also can see the same condition, but for the converted wave. So we can see the asymmetry here, the incident P wave and the reflected S wave. And we can see the S wave does not propagate through the water. Well, the model number 1 is that one I just showed you. So we obtained the travel time curve with the automated peak, and we can see how it worked. So for no noise situation and for 90% signal noise ratio situation. So we can see for both conditions, the automated peak could work very well. So we can see the conventional reflection, the incident and reflected P wave, and the incident P and reflected S wave. So we can see both non-hyperbolic events. However, this one is more non-hyperbolic. And then we can see, even with a strong noise, those informations could be recovered. For the second model, is also a carbonate reservoir, but with a thicker anhydrite structure, but also around 2 kilometers of salt. And then we can see the variation concerning the ray tracing. But it could also be, the parameters could also be obtained, and we could pick the travel time for this kind of event. The third model, also a carbonate reservoir from Pre-Salt, but we have abnormally lower velocity because we have an inversion of the sequence of the different kinds of salt. So we have an anhydrite, then a halite, and an anhydrite again. But the carbonate reservoir, and then the carbonate reservoir, and we can see the variation of the ray tracing. Even with this different kind of structure, we could also recover this kind of formation and then obtain the target reflection. Well, the model number 4 and the model number 5, they are not from carbonate reservoirs. They are sandstone reservoirs sealed by shale. So a thin layer of shale here, and then the sandstone reservoir. We can see the complexity of the ray tracing is not so they're not so complex as the other, but it's very suppressed compared to the others. But if we analyze the obtained reflection here, we can see it's not well picked for few points in the beginning. As we can see, it's not right, not exactly right. For this part we can correct, but starting from around 7 kilometers, we can see it's completely it was wrongly picked, so it couldn't recover the travel times for more than 7 kilometers. So we could determine it's not working very well for this kind of model. And similarly, we can see another sandstone reservoir sealed by shale, but it's even shallower. But it couldn't, the algorithm couldn't work very well for this kind of model too. So we can see it's not right for the P wave and for the conventional reflection and for the converted reflection. However, the same information is obtained even with noise. Well, the PVO analysis, we tested other models. So they are near surface models, and we can see the reflection, and with a critical angle around 37 degrees. And this one, this first model is presents a Ricker wavelet, while the second model is the same one. However, it was modeled with a semi-Gaussian wavelet. And the model C is with a critical angle of 30 degrees, and then the model D is presents a 44 degrees critical angle. Well, so what can we obtain with this performing the PVO analysis? Performing the inversion for the signal for each trace, we can see that the highest frequency and the highest amplitude are related to the critical angle, because the critical angle here is 37 degrees. It can be explained by the separation of the reflection and the refraction. So the refracted wave here and the reflected wave here, we can explain this. This can generates a higher frequency and a higher amplitude, especially at this part. However, it does not happen. We cannot determine that it happens always, because we don't have specifically mathematical description. We cannot analyze. We cannot determine it analytically. So we must observe the global minima. So the quality of the fitting. So the error we could find for each trace during the inversion of this trace. So we can see the worst fit, the highest global minimum, is also related to the critical angle. However, it can be explained mathematically, because the mathematical definition we are using here describes the Ricker wavelet, and we must remember when we reach the the critical angle, we have a phase shift. So it's the most discrepant moment concerning the Ricker wavelet once the wave started as a Ricker wavelet. So for this kind of phenomenon, we have that it can be considered constant. So the critical angle must be related to the highest global minimum. Well, for the other two models, we could find the same. So for a lowest critical angle, for a lower and for a higher critical angle, we could find the same condition. So it's not a peculiarity of 37 degrees of critical angle or concern the model. It really happens other times. So we could determine that valuable technique to find the critical angle without information of velocity, without performing the velocity analysis. So we can find the critical angle before finding the velocities, and then it's important because we can calculate the Poisson ratio or other kind of information without performing the velocity analysis. So that's very interesting. Here's just to show the critical angles are really these angles. And it's the forward problem. So here it was calculated with the Zucker's equations. So we can find for the first model almost 37 degrees, and then 30 degrees, and then 44 degrees of critical angle, of course. Well, after performing all of this, we can apply to the calculation of each non-hyperbolic equation. So at first, the hyperbolic equation was tested, but it was tested just as a comparison effect. Once it's not able to control the strong non-hyperbolicity we are working here. So it's just to compare how non-hyperbolic the event is. Well, the shifted hyperbola was proposed by Malavichka, and he proposed the S parameter, which determines the heterogeneity, and then it relates the real interval velocity of each layer to the RMS velocity, as you can observe here, and then we find the S parameter. Al-Khalifa and Tsivankin proposed an approximation that considers the anisotropy. We're not working with anisotropy here, but this equation is commonly used by the industry. So it's interesting to test it for the models we're working here. And it uses this eta parameter that describes the relation of the anisotropic parameters proposed by Thomson. Well, we have also the equation proposed by Yurzin Stovas to be used for VTI media. It also uses the S parameter proposed by Malavichka. And Blia's equation was proposed also to use the same S parameter for heterogeneous and VTI media. Moody-Dillinger proposed the use of this F parameter. This parameter describes how discrepant is the wavefront starting from a spherical to an elliptical shape. And Li Yuan proposed to use the gamma parameter as a relation of the converted wave and the conventional event. So it considers the conversion point and it can describe the heterogeneity and the wave conversion. So it can deal with two conditions at the same time. And it presented to be a very general equation in previous works, not only from Line 1, but previous works of mine, including my master's. I showed this is a very general equation. So it worked very well for complex models and for complex situations. So the proposition here is to generalize the Line 1 equation to consider the OBN condition. So it was generalized to consider two more parameters, but they are a priori parameters because they are just considering the difference of that and considering the water layer and the velocity of P wave in the water. So it was also simplified, the hyperbolical part, because for ultra deep reservoirs, this part can be simplified. And of course, they share the same origin, so they are very similar and working very well. But we can see for onshore models, this part of the equation can be disregarded. So it becomes again the Line 1 equation. So the variation is considered only for offshore models. Well, so the forward problem can be described as the structure. So we can the wave propagate through the geological structure and then generate this kind of ray tracing, and then we can find the reflection, the reflection event. So the inverse problem is can be described as the reflection, and then we use the automated peak to obtain the travel time, curve, and then with this information we can find the position of the carbonate reservoir. Oh, I'm not talking about too much about the optimization algorithms because I didn't develop them. Of course, I just tested several algorithms, more than 20, before determining these 5 are the best for this kind of problem, and they are very interesting to be compared among them because they are very different and they provide different kind of benefits. So we can we used the IMFIL, implicit filtering algorithm, to consider a local search, consider a bound constraint, of course, and def-min search, the classical Nelder-Mead local search optimization algorithm based on simplex, a particle swarm motion algorithm because it considers the many points to be calculated at the same time. These first 3 algorithms are local search, and starting now with the MCS as the global search optimization algorithm, it's based on dividing the sampling space in smaller spaces. So we get all the data set divided in small spaces, and then you apply a local search to each small space, and then you are going to combine the other spaces until you find the global condition. The TONLab LGO, it's a mix of global and local optimization algorithm. It's a combination of a Lipschitzian Brentano bound and a deterministic and stochastic search. Wow, so an interesting analysis here is the use of L2 and L1 norm, because the automated peak allow us to obtain the travel time curve, so we can use the least squares and not only the semblance function. So it's very interesting because we can obtain much more information with the difference of the L2 norm and the L1 norm. Both are very interesting. They're minimization functions different from the semblance, but actually semblance a maximum function, not a minimum, but they're both to find the best solution. However, with this kind of analysis, we could find much more valuable information. So the L2 norm presents a more a softer variation, while the L1 norm presents a more abrupt variation, and we can see it later. Well, the objective function analysis defines the quality of the solution related to its variables. So we can see here the velocity, and then the third parameter, the heterogeneity parameter. So for Lin 1 is the gamma, for Khalifa and Tivankin it's the eta parameter, so it varies depending on the equation. And the third dimension in the hyperspace, we have these contour lines, and this is a veil. It's not a mountain. It's just because we're looking for the minimum. So here is the lowest point, so the lowest minimum value. This kind of situation, you have a unimodal condition. So there's only a global solution. And here we have more than one solution, a more complex situation, and we have local minimum regions. There are also mathematical solutions, but they are not the best ones. And of course, they cannot represent the reality of the problem. So we must always find the global minimum region. Well, the comparison among the equations must be performed after calculated. Then we can compare to the observed event. So we calculate with each equation, with each multiparametric hyperbolic travel time equation. We compare them to the observed event, which we obtained with the automated picking. And then the approximation which presents the lowest error, so the error closest to zero, is the best option. This is from a previous work. It's not results from this work, but it's just to illustrate. I will show you the related results. So for the first model, I'll focus for the first model because it's a very conventional model of the pre-salt from Santos. So for the Malavich equation and for the P wave, for the conventional event, we can see a very simple topology. However, for the converted event, we have the same topology. It does not vary the structure of it, but it is displaced, and it was already expected because the variation of the parameters are due to the variation of the velocity. So the velocity and the additional parameter must change. So, but it's not structurally different. However, varying from the L2 to the L1 norm, we have a more abrupt structure. So the maximum is much higher and the minimum region is much lower. And we have a narrower minimum region. So a narrower minimum region allows us to obtain a more accurate result. And more discrepance and a higher discrepance between the maximum and the minimum allow us to use the algorithms in a faster way because they could find the minimum quickly because of this kind of discrepance. The Khalifa-Tsivankin equation presents the same kinds of variations from the conventional to the converted event, and from the L2 in comparison to the L1. However, the structure is absolutely different from the Malavichka. So we can, and it should be, it was expected to be very different because of its mathematical differences. So we describe and we're mapping the behavior of the equation here. Ursin-Stovas presents an equation with the same kinds of variation. It's not so simple, the structure, but it's more complex than the others. But presented the same variation, the same kinds of variation. The equation proposed by Blies presents a little more complex topology, so it's a little more complex, so it needs to use sometimes a more robust optimization algorithm, even it being unimodal for this kind of problem. We have the equation of Merdin-Dillinger, and this equation is much more complex considering the objective function, the topology of the objective function, but it is multimodal, so it presents also a local minimum region. So another solution that we don't want. The variations are very similar considering the positions. However, it presents a changing behavior considering the global and the local minimum region. Because when you have the P wave, the conventional event, we have the global minimum region here, and for the converted event, we have the global minimum region here, exchanging its position with the local minimum region. So it's a big problem because we can many times find the local minimum region, and it will be hard to describe if it's the local or the global minimum region. So we need to use a much more robust optimization algorithm, which takes much more processing time. Then the UM approximation, it's not so complex topology. However, it presents a local minimum region, not only global. But the variation of the structure is very similar to the other equations, to all of the other equations. However, it does not present any kind of changing position stuff, you know. So this kind of problem is not found here. With this kind of analysis, we can observe many interesting things also. Because with this kind of condition, we know where we can find the additional parameter, the gamma parameter, the value of the gamma parameter that we don't want. So we can find always the local minimum region is lower than 1. So we can, in following processing steps, or next time we're performing the inversion, we can disregard any kind of value lower than 1. So another important analysis that we can perform with this kind of study of objective function. And another interesting thing we can see here is, if you remember the Lie and Yuan approximation, if the gamma parameter is equal to 1, we have the hyperbola equation. So all the non-hyperbolic part of the equation disappeared. So we can see for one, we never have a solution because it's always between the two solutions. So it's very interesting to observe here. And the proposed generalization of Lie and Yuan approximation showed a very similar structure. However, it's much more sensitive concerning the velocity. So it's very interesting because we can see Lie and Yuan approximation are more proportional. The sensitivity is much more proportional comparing the velocity and the heterogeneity parameter, the non-hyperbolic parameter. And here we can see a more discrepant sensitivity. So it's very interesting because we can find velocity information more accurately. And as I already told you, they share the same origin, of course. So the main characteristics are the same. So multimodal, and then the same structure, topological structure very similar. The peculiarities I told you about gamma closest to 1, or to values of gamma lower than 1. And then comparing the equations. Well, using the IM-Field optimization algorithm for the conventional event, we can disregard the results of this equation, the hyperbolic equation, because it couldn't fit. It fits only in 2 points, of course, because it's not a hyperbolic problem. But we can see that the black line, the proposed generalization, and the red line, leading one, presented respectively the first and the second most accurate results. The same for PS. However, once the PS is more complex, the converted wave, the converted reflection is more complex than the conventional one. We have this kind of increase concerning the travel time error. And comparing the L2 norm to the L1 norm, we have the same kind of variations, just excepting by the L1 norm, we have a lower residual error. So this relative travel time error decreases with the L1 norm. And we can remember now what I was talking about, the objective function when we're using the L1 norm. We have a narrower global minimum region. So for this reason, we could perform it more accurately. So the L1 norm allows us to obtain a more accurate result. You can read the exact values in my thesis, but the average of them is around 10 or 11%, as you can see here, comparing around 6% to 6.5%. With the F-min search optimization algorithm is the Nelder-Mead optimization algorithm. We can see the same kinds of variations, just varies a little more. One algorithm, one equation to another varies a little in few points, but essentially the same set of results. However, it's a more complex optimization algorithm than IM-Field. So it provided a more accurate result. As we can see, the relative travel time error is lower. And the same kind of variation we could find with particle swarm motion algorithm. and we can see as it's more complex in comparison to the previous two algorithms, we can see the quality of the results significantly better. So, and using a global minimum region, a global search optimization algorithm, we can see an even lower error. And then with the most robust algorithm tested here, the error of the proposed generalization and Lie equation, we can see it's almost zero. So it's almost perfectly fine found. Well, this part we can see the processing time. So if you compare the less complex to the most complex optimization algorithm, we can see the variation of processing time increasing significantly when you reach the TONLab LGO. The L2 norm presents a more subtle structure variation, so we have more processing time to obtain with L2 norm in comparison to L1 norm.
So, Nelson,
Wait.
sorry, you have 10 minutes up to finish.
Okay, thank you. Well, and then in comparison to L1 norm, we have this difference of processing time. And the converted event, of course, is more complex, so the processing time is always higher. Disregarding the results of the hyperbolic equation we have, we must compare the other non-hyperbolic multiparametric approximations. So the Lie one presented the best to be the most efficient in comparison to other equations. And the second best was the proposed generalization. Well, for the model 5, I just want to quote the two different behaviors for Ursin-Stoffels equation and Blia's equation. It happened for model 4 and model number 5. Remember that I told you these two equations are unimodal, okay? But for the model 4 and model 5, they are multimodal. They presented local minimum regions. So this binary behavior can complicate the analysis for this kind of equation, because we never know if it's local and global. We can map this variation. However, it's hard to determine a priori. However, using the L1 norm, it does not also makes the structure more discrepant, but it also attenuates some features, as we can see here, due to the higher discrepance. We can attenuate few features that starting to appear at few parts of this kind of equation. So the L1 norm, we can suppress these regions and make the local minimum regions disappear for this equation for Ursin-Stoffels, and we can see the same for Blia's. So we have here the local minimum region with L2, and for L1 we don't have, because this part is almost disappearing. So the L1 norm is a strong way to deal with this kind of situation. Well, I start with three main conclusions. The automated travel time peak works very well to obtain the reflection events related to the interface between the top of the reservoir and the bottom of the south, even with a high signal noise ratio, which makes it an efficient tool to be applied for pre-south data. But we already know that it cannot be applied for every kind of geological structure, as I showed you for the sandstone reservoir with sealed by shale. The PVO analysis by the spectral recomposition demonstrated to be very effective, very efficient. It's not because it takes with my computer 7 seconds to perform the inversion for each spectrum, so it's very efficient. And concerning the effectiveness relating the processing time and the quality of the result, it's also very good. And we can obtain the information of critical angle without necessity of finding out the velocities. And talking about the equations, the two most effective equations here, the difference and similarities between the proposed approximation and the one proposed by Linear one, of course, are given by the fact of they have the same origin. However, their mass velocity and the gamma parameter are proportionally sensitive for Linear one approximation, while for the proposed approximation, it presents a much more sensitive mass velocity. So we can recover it in a better way. The converted event presents a more complex, a higher complexity to be calculated, of course. So it will take more processing time, and of course, the quality of the result must decrease. So it's not. It will happen. You cannot control it. The variation between the approximations presents very different topologies among each other, and it was, of course, expected, but we could find many interesting information with this kind of analysis. The variation between the norms, so it is an important information, because the L1 norm showed that it could make the global minimum region northward, and attenuating some features, what makes the analysis of Urzin-Stova's equation and Blia's equation more effective. We could determine that the Malavichkal Khalifa are always unimodals, and we can treat Urzin-Stova's and Blia's equations unimodal once since we use the L1 norm. And multimodals, Morin-Dillinger, Linear one, and the proposed generalization. The variation of the topology of the objective function is function of the approximation, model, event, and norm, in that order. Well, the best results concern the accuracy. You could see the proposed approximation and Liu one approximation. The accuracy, of course, decreased, as I told you, for the converted event in relation to the conventional event. The L1 norm showed to be more accurate by using all optimization algorithms that we tested here in comparison to L2 norm, and it's related to the fact of it presents an overall global minimum region. And the results concerning the accuracy for the optimization algorithms, it was what I was expecting, because the best results are related to the most complex optimization algorithms, the most robust ones. The best results concerning the processing time, we can disregard the hyperbolic equation, and then we can find the Li and Yuan approximation is the most efficient, and the second one is the proposed generalization. The algorithm is concerning the processing time is the inverse order of the accuracy, because the least complex algorithm will present a lower processing time. And the processing time is higher for the converted waves and for the L2 norm in comparison, respectively, to the conventional and the L1 norm. The topological analysis show to be even more important after the study of the norms, because mainly concerning the equations which present a binary behavior, such as Urzin-Stova's equation and Blia's equation. And the L1 norm presented very good results. However, it must be used only together with free derivative optimization algorithms. So the final conclusions are actually suggestions, because in case of using a unimodal approximation, when we don't need to use for a very high accuracy, we can use the fmin search. That's a good optimization algorithm, and it presents a very low processing time. And we can use it together with Malevich approximation, because it presented a very good processing time, and it's unimodal, so we don't need to perform a multi-start procedure, applying the algorithm several times. So, however, it's of course limited considering the accuracy. The optimization algorithms, I suggest to use the MCS, because it's quite good in comparison to TONLab, because it's not it does not present a significantly lower accuracy, but it's significantly slower to perform. It's significantly faster to perform the inversion. And when we need when it's demanded higher accuracy, we need to use. I suggest to use the proposed approximation, the proposed generalization of Lie and Yuan approximation with the MCS optimization algorithm, because this approximation is not significantly slower than the original Lie and Yuan approximation, but it's much more. It's a little more accurate in comparison to it for this kind of problem, for this kind of geological structures. So here are the references. If you're interested in anyone, you can ask me for it after the revision. And thank you very much.
Okay, Nelson, thank you for your interesting presentation of your results. Sorry, I had some problems with internet connection in my house, and now I am using my cell phone, unfortunately. Okay, your the presentation was up to 60 minutes, according to my calculus. It is good, because you stayed between the limits established by our postgraduate program. And now we can start discuss your presentation by a member of our examination committee. And according to our schedule, I would like to give word to the Professor Ranajit Ghose from Delft Technical University.
Professor Priimenko, if you allow me a comment.
What?
Just a comment, if you allowed me. It's I don't know if Professor Ranajit and Nelson need a short break before start, or it's okay to start now.
No, it's I don't know.
No, just Nelson and Ranajit don't need a short break before the.
We can.
Yes, we can give a short break time. Yeah, I am agree. How many?
Ranajit, 5 minutes. 5 minutes.
5 minutes. Okay.
Break. Okay.
Okay, 5 minutes. Okay, thank you. Ok, Renato. Vamos começar daqui a pouco. Desculpa, porque o internet na minha casa, tá? No final da apresentação dele, caiu. Ele levou um pouco de tempo para começar a usar o meu smartphone. Mas isso, infelizmente, às vezes acontece aqui na nossa região.
No, okay. We can start now. Ranajit, your sound is.
I'm sorry. Now you can hear me, I'm sure.
Oh. Okay, let's start now.
Okay, Professor Priimenko, thank you very much for inviting me, and to all of you, thank you for having me in this meeting. And dear Nelson, it's an honor to be in your PhD thesis defense committee.
Thank you.
I have read your thesis with much interest. I commend you for this research and the thesis that you have produced. Your research is really focused on non-hyperbolic reflection move-out, and more specifically, to best fit the move-out and get a better and faster velocity estimate using a generalized formulation without having to bother about the cause of the non-hyperbolicity, as you call it. In that sense, it's a very practical work. I think it's important to place this research in the correct perspective. You just showed in your slides, there are some 8 or 10 different models that you looked at, and you have cited and made use of many of them, like Malovichko, 1978, Muir and Dellinger, 85, Slotbaum, 1990, Chavanking, Thompson, 94, and so on. The list goes on. But still, all of these models that you have considered are related to non-hyperbolic velocity move-out. I realize that quite a few work has happened about generalizing this thing as you have tried to do. And I was looking desperately for references of those work, the work where people have really tried to generalize the non-hyperbolic move out. Just to mention a few is the work that has been done in Stanford University by Gonzalez Serrano and John Claerbout and published in Geophysics in 1984. And the title of the paper is Wave Equation Velocity Analysis. It's a very classic work about trying to fit non-hyperbolic move out using a generalized theory. Then the work of Ali Nauruzi, which is also published in Geophysics. The title of the paper is Generalized Form of the Dix Equation for the Calculation of Interval Velocity and Layer Thickness, and it was published in 1989. Then the paper of Sain and Kaila, which was published in Geophysical Journal International in 1996, where the title of the paper is Direct Calculation of Interval Velocities and Layer Thicknesses from Seismic Wide Angle Reflection Times. And there are many more. All these studies are about generalizing the Dix equation and all subsequent equations, including Chavankin and Thomson, Slotboom. So I was just wondering that why these references are missing in your paper, and maybe you just overlooked it, but in case you need these references for your future publications, I will be happy to provide you those things, but it's just for the sake of perspective, to put your research in the correct perspective, that there have been significant work in the past where people have tried to generalize these different work, different formulations, and unfortunately, I missed them in your thesis. Do you have any comment on that?
I don't know all of them, but I think the three first you quoted, I already tested. I tested it, I think, in 2014 or 2015.
But it is not in your reference, the John
Yeah,
Claerbout.
I know, because I selected the equations, the 6 equations which presented the best results in previous works of mine. So that's why this kind of approximation, I didn't use it here. I agree. I think it must be quoted. It must be in the references, and maybe a paragraph speaking why they're not being used here. But the results of them are concerning the processing time. They're not so efficient. It's similar to another equation that's very good concerning the accuracy. It's the Sergei Fomel equation. However, it uses many parameters. It can be simplified to have only 3 or 4 parameters, but when you simplify it, the processing time increases, does not decrease significantly, and the accuracy increases, decreases a little. So that's this kind of behavior is the same I saw in 3 of the equations you were talking.
Okay.
So that's why
okay. Fair enough. It's just that I am saying that you do not have any reference of the paper of Al-Nouruzi, Sain Kaila, John Claerbout. These are very well cited papers, and these are nothing to do with accuracy and speed of calculations. For a PhD research, it's extremely important to have the perspective of the research. What has happened in this, what other people have tried to do. In that sense, I discussed it. It's not that you can be selected about some papers, just exclude some papers because they're less accurate or taking more time. My intention to mention this work was that it is important to give a proper perspective of research that has happened in generalizing the non-hyperbolic move out studies. That's all I wanted to say. But anyway, it seems you are aware of this work. So I just think it is important to discuss and refer these works and try to say why you excluded them. So you just gave me answer. So this was just a very starting simple comment from size, not a big criticism. I was just looking for these works because this is not a new research topic in any sense. So I was just curious that why these are simply missing in your work. My main question comes from the following, that in several parts of your thesis, firstly, for instance, page 44, chapter 1, is it by any chance possible to put the page of your thesis on the screen?
Yeah, I will.
We can all see then.
No. Can you see?
Not yet. Yes, I can. If you
Now
please go to page 44, please.
page 44 here.
Yes, and it is the first, second, third, fourth paragraph where you write, the vertical heterogeneity combined with the long offsets between the source and receiver is another factor able to generate a non-hyperbolic event once there is a difference between the interval velocity and the RMS velocity, and this error increases on larger offsets. You use the word this error, okay? And then I move on to page 79, chapter 4. Can you go to page 79?
79 here.
Nelson, could you make bigger the page, please?
Which paragraph?
If you go to page 79, I'm just telling you, it is the last paragraph.
This one?
Let me see. Yes, I'm just looking at it. Just give me a second, please.
Okay.
Yes. Yes, the last sentence actually of this paragraph, it reads that, however, once it is necessary to model structures with geometry of acquisition where there is a difference of datum between source and receiver, it is also necessary to use a more complex tool as the software of 2D finite difference modeling. This, and there are many other places actually. For instance, once more, I can say, if you please go to page 52 on chapter 2.
52. Here?
Yeah, and there you say at the last, where you RMS velocity at the lower part, you say the RMS velocity is the quadratic mean of the interval velocities. As during the seismic processing, the RMS velocity is used, it is natural to have an error associated to the difference between the RMS velocity and the set of interval velocities. This error increases while the offset is increased, and then for offsets larger than the reflector depth, the hyperbolic approach is not valid. And my question is that it's about the use of the word error. I think it is just more than obvious that at far offset, the RMS velocity and the interval velocity, if you use Dick's equation, you can get an estimate of RMS velocity, they will certainly mismatch. This is nothing to be, it's not an error, it's a deviation, because Dix equation is based on the assumption that you should use Dix equation only for the near offset, actually ideally for zero offset. For zero offset trace, you can use that equation to get an approximation for the RMS velocity, and that it doesn't hold for far offset. So I was very surprised that why should you use at all the interval velocity to check your RMS velocity at far offset? Why should you at all try that?
I'm not sure if I understood your question, but you mean why calculate the RMS velocity and compare it to the
interval velocity? You all through your thesis, your last results, your figures, everywhere, you said interval velocity, and you are checking far offset. And I simply don't understand why RMS velocity, particularly in the far offset, can be obtained from the interval velocity. Dix never claimed that. Dix strictly said, Dix paper 1955 and all paper, that this is really valid for zero offset, at best at near offset. Don't try to fit this equation for the far offset. That is the definition of Dix equation. And I'm surprised to see that in your far offset, you are using interval velocity and you are saying this is error. This is not an error. This is expected. This is the definition of the Dix equation.
Yeah, so, exactly. But I mean, the importance of trying to use more further offsets, it's because we can obtain more a better stacking in the future. So that's why I try to perform the curve fitting for larger offsets, even when the RMS velocity is so different from the interval velocities, and that's why I try to use different approximations and to test which one or which of them could perform this fitting, could control this behavior.
No, that's fine. I mean, about your approximation, I'm not talking about them. I am only talking about using interval velocity to check your far offset, okay? I'm only saying that when you use interval velocity and try to use interval velocity to get an estimate of RMS velocity, and you use basically Dix, but when you use approximation, those are of course specifically made to explain non-hyperbolicity, as you call it. Huh? So those I understand your reason. I agree with you that there is some sense of checking that. But I personally have difficulty to appreciate in all your figures, if you go to your thesis, and if I go to your figures, for instance, all the figures that you have in the last part of your thesis, and it starts from your I'm going to your figure. It's
page 187.
Yes, possibly that's right. I'm just going because I have the digital file, and I'm just scrolling. I am just something like that. Yes, exactly. 187. And in your talk, you actually mentioned this is. I would rather get rid of that blue dashed curve. It makes no sense to me to put Dix 1955 and calculate far offset and saying Dix does very bad. I mean, I think anyone will not agree with that, because this particular equation is not meant to be compared in this way.
Oh,
do you
yeah.
agree on that?
No, yeah. I just put it to as a comparison effect, just to show how the problem is non-hyperbolic. Because if we compare with other problems that show...
I understand. Maybe that's not a fair place to put that one.
No, I agree.
Okay.
Maybe,
good.
I think for the figure, it makes it more...
So, okay, so that's clear. We both agree on that. That is possibly not the best way to put that curve on top of all other curves there.
Okay.
This brings me to the next question, and that is actually the most fundamental thing. And I was, while reading your thesis and listening to your presentation today, I was really thinking deeply about the basic idea behind this research. You compared the performance of your generalized scheme and that of Lee and Yuang. They did better in terms of fitting and Al-Khalifa and Chavanking and Leon Thompson, etc. They did apparently worse. Of course, that's again another discussion. But if we assume that your results are correct, what does it say? I mean, my main question is that these guys like Chavanking and Thompson and Al-Khalifa and Chavanking, they have a physics behind. The physics is that of anisotropy. In case of, you didn't refer to, but I saw this paper of Stanford group. They really talked about vertical heterogeneity in velocity, the group of John Claerbout. And they have a physics behind their formulation. That means their intention is to understand a cause and how that cause has contributed to non-hyperbolic nature of the move out. And your argument is, I don't care for the cause. I don't at all care for, because you have considered three different reasons that may contribute to hyperbole. Very clearly, you have considered vertical variation in velocity. You have considered OBN geometry, and you have considered converted wave. And you said, I don't care what is the cause of it. I just want to fit the curve. Just imagine if you have an anisotropic formation, okay? And you are fitting the curve without having the Thomson parameter delta and epsilon. And you claim that my generalized formulation has fit the curve better, okay? Does that mean the velocity estimate you have got is better because you have ignored anisotropy? Suppose in the nature, in the true nature, in the subsurface, the medium is anisotropic. It is highly possible. There are a lot of previous study which has said that isotropy is a singularity. Anisotropy is a much more realistic situation. However, you, for the sake of fitting your curve, say that I have a generalized formulation which is very applicable for anything and it fits my velocity very well. However, that velocity which you are getting by fitting that, because it doesn't have any physics, it is completely ignoring the actual physics of what has created that non-hyperbolic nature in the subsurface. As a result, your estimated velocity value would be not correct. It may not be correct. It may not be correct because you have ignored the physics. You understand my logic, Nelson?
Yeah, I do.
So let me finish this part. I understand you are developing a very practical technique. You are claiming I don't bother about what has caused my non-hyperbolic move out. It may be converted wave, it may be OBN geometry, it may be vertical thing. You go far offset, it creates. So I fit the data very well and it's very fast. But realize there is no physics in your way of handling the move out. You are just doing the kinematics. And because of ignoring physics, your estimated velocity value and layer thickness, and finally the imaging itself, because you use that velocity to stack your data, to do migration, to image. So there's a nice saying that a beautiful image is not necessarily the correct image. This is any experienced seismic processor knows that. I can do a beautiful filtering and processing, and my image will look very beautiful. Does not mean it represents the true nature. So my question is that when you get a velocity by a very good fitting, does it mean, is it the correct velocity in the nature if you don't have a physics?
Well, actually, we know that for this kind of problem, we have the non-hyperbolicity originated from the combination of all of this I showed you. But we cannot describe how strong each part of it. So we can characterize the non-hyperbolicity. We can describe how non-hyperbolic is the problem. We just cannot describe each phenomenon which and how each one is influencing the non-hyperbolicity. Because for a stratigraphical analysis, the most important formation is the velocity. However, for the geological characterization, I absolutely agree with you. It could be a little poor to describe the geology, because we are disregarding many important information. But the focus here is to describe essentially the stratigraphy. So that's why I can disregard the influence of each no hyperbolicity. So we can all these equations consider the velocity, and they try to describe a physical property. But also, even in a problem like a structure with anisotropy, if you apply the Al-Khalifa-Vankin equation, the eta parameter, the anisotropic parameter, couldn't describe exactly the reality. Because the non-hyperbolicity is not only originated by the anisotropy for the problem I am making this hypothesis. So how could you say that the anisotropic parameter could describe exactly the anisotropy? Of course, it could describe a strong influence of anisotropy. However, it could describe exactly. So it's not the real anisotropy, because it can you can obtain other kind of effects. You can suffer with other kind of effects that makes the event non-hyperbolic. So yeah, that's what I'm doing here. But I'm disregarding more original effects. That's why
it is not a question of, this is a very well studied topic, and the people who have done substantial work on non-hyperbolic velocity move out, they have shown time and again that neglecting completely the physics is detrimental to the purpose of seismic investigation, in the sense that fitting the velocity move out is one purpose of the exercise, but also to address the geological problem of the velocity itself, because your velocity itself is wrong simply because you force to fit the curve. Your velocity value does not represent the natural reality, and so you end up getting an answer which is wrong. And so all I was trying to say that it is important to realize that best fit curve does not represent the correct curve. That's, you agreed actually, but anyway, I just wanted to point out that this, when you try to publish or something about this, maybe you should be prepared to address this basic question behind this approach, that how a generalized approach which ignores any physics. It doesn't mean I'm advocating that you look for anisotropy or you look for no, but give that margin of error that your estimate of velocity may not be and possibly is not the correct velocity. So when you are doing a forward modeling and synthetic data exercise, that's different study. But in nature, you don't know the true velocity. And by virtue of fitting your move-out curve using your generalized formula, if you claim that that has fit the data better, and therefore that's the velocity, that is just too simplistic. That may not be the correct answer. That's all I'm trying to say. Do you agree on that?
Oh yeah, sure.
Okay, then we can move on because we have limited time. I have a few other questions. If Professor Priimenko allows me to ask one or two more questions.
Okay.
Okay, so Nelson, we move on to your page 270, figure 287.
270. Okay.
Yes, it's a bit familiar to me because at that time you showed me these things you were in Delft.
Yeah.
So what I am curious, Nelson, is this lower plot of transmission coefficient is already normalized or not? The reason I'm asking this question, let me tell you very simply why. Because after the critical angle, I see your reflection coefficient goes to 1, which makes sense to me completely. But your transmission coefficient takes quite a few angles to get to 0. And then there's somewhere energy is not being conserved. I expect your transmission and reflection coefficients together should be 1. Why your transmission coefficient is non-zero when your reflection coefficient has become 1?
The reflection is normalized, but the transmission not, because it was just for the scale.
but then this variation, I mean, that's okay. I mean, that's exactly what I thought. I expect if it is normalized, at least in the same scale, it should go to 0. Do you agree? Because your reflection is, I cannot see because there is no resolution, but it looks like it has reached 1 beyond critical angle immediately. So in that case, the transmission coefficient is taking some time, some angles, slowly, gradually going. That gradual change to 1, I don't see in reflection coefficient. So what's happening actually?
Well, this one is just I calculate the forward problem here, and I used the Euclid's equations. But I'm really not sure why this behavior is exactly like this. But I thought it was about it was because I normalized the reflection coefficient. And you're talking about this part?
No, not at all. I'm talking about post-critical. You see, post-critical, your reflection coefficient is 1, isn't it?
Yeah.
Which makes sense because you have a total internal reflection.
Yeah.
But your transmission coefficient is still not 0. It should be, because your total energy is conserved. Huh? You have a incident wave, you have reflected and transmitted, and everything is being reflected. That's why you are getting 1. But your transmission coefficient, there should be nothing transmitted into the second medium.
Okay, it should be 0 starting by here, right?
Yeah, I mean,
yeah, no, it's because the normalization and it's calculated separate.
Yeah, I was just thinking it looks a little bit strange because it's a kind of gradual. Even if you normalize, I see some kind of. So I was curious. I mean, it just makes a little bit strange feeling to me that even if you normalize, it doesn't look like something strange is happening, because we do always full Zoopris inversion a lot. So this it happens. It happens like that. So something is. I was curious. Well, let me move on to my next question. Just a few. This PVO analysis, the phase variation with offset. This is to me very interesting, and I remember this is also something you were in Delta at that time, and so I am very happy to see these results. But I want to discuss with you one thing, Nelson. That is, I hear a noise though. Is it my microphone?
I think it's not. I hear nothing.
Someone else's microphone. Do you know where it's coming from? Can it be stopped? Yeah, it's gone. No, not yet.
Wait. Can you hear it? You're still hearing the sound. No, everything closed. So.
So anyway, RG, my name is Ranajit. So RG is just last a few questions. Nelson, what I was actually very curious to discuss with you is you are fitting a Ricker wavelet, and when you are coming to the critical angle, you see that the wavelet changes to Gaussian, isn't it? You have to now turn your microphone on. Yeah.
No, it does not change to Gaussian here.
No,
no
you use your Ricker wavelet, and then you do a spectral decomposition. But when you cross the critical angle, then the match you find best match, that is with a Gaussian wavelet.
I'm sorry, after the critical angle.
Yeah, you have written in your thesis, and we discussed in the past also, the wavelet changes to Gaussian, the similarity with the wavelet.
After this,
you have written in your thesis. Shall I show you?
Can you tell me the page, please?
It's in your PVO analysis. If you go to your PVO analysis, PVO analysis part. Can you go to your PVO analysis page?
I'm going to. Mm. The automated picking, or after here the PVO analysis to find critical reflection.
Okay, excuse me, it's not on the screen. Yes, so you see, it's just the last few lines. You are writing here. However, in a condition when there's a phase shift, the Ricker wavelet is gradually distorted. So it's the 6th line from the bottom. Into a semi-Gaussian wavelet. Once the phase is getting shifted, the observed wavelet is becoming more disparate from the Ricker wavelet and becoming closer to a semi-Gaussian wavelet, which results in a higher global minimum value. It happens because the error of the calculator, that's obvious, that you get a maximum. You also explained in your presentation. Can you go to the next page now? And the top, the spectrum is being used to calculate the spectrum of the wavelet. So my question is, can you explain me why it becomes semi-Gaussian? Do you have any idea why it becomes semi-Gaussian?
Why it ceased to be a Ricker and start to be a semi-Gaussian? That's the question.
My question is, why the Ricker wavelet gradually changes to semi-Gaussian towards the critical point? As you have found in your processing, you have found that, but there is no explanation for it. And I'm asking, do you have an explanation for that?
Mathematically, I think it's because when the phase varies, as we can see the definition.
That one you explained. That one you said is your phase varies, your phase goes to 180 degrees, so you have the maximum of the global minimum. That you already explained in your presentation, and you have written. My question is different. My question is, why Ricker wavelet changed to semi-Gaussian?
Physically, why? The energy involved in the spectrum maybe concern the separation of the reflection and the refraction. I think the energy concerning the oscillation, once they are propagating in different velocities, they start to being separated in time, and then it's a consequence of the energy being separated. I'm not sure of that, but
well, the Gaussian, as you know, in probability theory, in the probability statistics, probability theory, if you take a probability density function of many random pulses, then as your number of pulse increases, the probability density function takes the shape of a Gaussian, isn't it? In the basic probability theory. So there is something in the seismology, it's called limit theory. In the limit theory, it says that if you bring many random waves in a very short spacing, for example, if you bring your layer thickness to very short, and if you send a transmitted wave through that, they will interfere and the distribution will look like a Gaussian. It is really the basic probability theory, which says that, and that is the limit equilibrium theory in seismology, which says, so what happens? I'm speculating, I'm just discussing with you, Delson. Maybe we can discuss afterwards more. But all I'm suggesting, that think that in a critical angle, your wave is going along the surface, and every point is the Huygens source. Every point is a source of a secondary wavelet. When you are at that interface, you have a wave where every point is the source of a secondary wavelet, and the wavelet is going upward. So you have a lot of closely interfering wavelet, which is happening at the critical point. So I can imagine if we solve this equation, we may find that the limit theorem is creating the shape of the Ricker wavelet to change into a Gaussian wavelet. I have a feeling that we can model it. So it's just I wanted to discuss with you. I will just finish my asking questions with just the last comment. And my last comment is that a PhD thesis is an important academic document for the posterity, and people will be reading it and using it in the future. Therefore, it should contain technically appropriate expressions. So one little thing is, let's go to page 43 of your thesis.
43.
Have you gone there? 43 of your thesis? And there you are writing. Are you there?
Page 43, is that one?
Yes, and you are writing, to record the seismic waves, many receivers are arranged on the surface and in different offset from the source. There are two kinds of receivers, the geophones, which are the receivers able to detect ground vibrations, and the hydrophones, which detect the pressure variation in the aquatic medium. Is a geophone is used to measure ground vibration, Nelson?
Sorry, is the geophone?
You have written there that geophone records ground vibration and hydrophone pressure. But what does geophone exactly measure?
You mean the electrical behavior of it?
No, not electrical. What does it mean by vibration? Vibration is a very vague qualitative word.
It's very generical.
No, not generical. What do we measure with a geophone? That's my question. What do we measure using a geophone?
Well, we measure the vibration.
A particle motion can have how many derivatives? If you do not do anything, what do you measure? Is a displacement. If you take a derivative of displacement, what do you get? Velocity.
Yeah.
Particle velocity. And if you take a derivative of particle velocity, what do you get? Particle acceleration. And all three have different sensors. When you measure acceleration, it is accelerometer. When you measure displacement, it is displacement meter. When you measure geophone, it is particle velocity. You cannot say just ground vibration using geophone. Your geophone doesn't, ground vibration does not say anything. On the one hand, you are writing hydrophone to measure pressure. You are correct. However, when you are talking about geophone, you are writing ground vibration. This is a PhD thesis. You have to say particle velocity, because geophone really measures particle velocity. It is not an accelerometer. This is just one simple example, but in your PhD thesis, there are many expressions. I can continue, but I will stop very, very, very simply. But for example, when you say vertical S wave and horizontal S wave to mean SV wave and SH wave, that is not correct. There is nothing called vertical S wave and horizontal S wave. It is vertically polarized S wave. S wave propagation direction is same, only the polarization direction is different. You do not call it vertical S wave or horizontal S wave. I'm just saying this because this is a PhD thesis. In the future, people will refer to your PhD thesis. So this is very minor comment, Nelson, but I'm just suggesting if you have chance to make a final version of your PhD thesis, you may consider correcting this thing. With this, I finish my defense.
Okay, thank you. I already noted it, and I'll perform these corrections after.
Okay.
Are you satisfied with the answers, Professor?
Just a moment. Okay, Professor Ranajit, many thanks for your valuable observation and comments. Without doubt, such kind of observation comments will be incorporated in final version of the PhD thesis of Nelson.
Well, I hope it will be very nice. But Nelson, at the end, I really absolutely want to congratulate you for this work. And I think it's a very interesting piece of work, very practical, and it will be useful.
Thank you very much.
Okay, thank you. Okay, let me give next talk to Professor Mitrofanov, Georgy Mitrofanov. Professor, please, your time.
Just a moment. Yes, I switch on my microphone. Yes, sorry. Yes, dear colleagues, it's very interesting for me participate this committee and meeting. Thanks a lot for Professor Priimenko that he invited me. Yes, for participating in this interesting work. And Nelson, I would like to congratulate
Thank you.
on completing and presenting the results of this work. Yes, this thesis a good impression on me, absolutely. I would like to note that three important moments in the beginning to which the author paid great attention. It is very important that he provided a detailed study of the methods of time recording in the subcritical and subcritical areas. Yes, it was interesting. Maybe yes, to listen some discussion about this question, but I think that you understand the complexity of this question, and this study shows that you have a deep understanding complexity such things and for real data processing. About it, I say yes, you use phrase the proposed automated picking technique was very important to conclude the main objectives in this work. The other proposed approach was also important to find other kinds, it's yours words, of information concerning the phase variation. As we understand now that this is variation of velocities, yes, for the ground, yes, phone, and the pressure variation for the geofond, and the phase changing, as my opinion, it's one of the important questions in modern time, because we have the very big distance as for the observation for the real systems, and they have the critical yes angles and changing the form of the seismic signals and the estimation this variation and for the accurate estimation time arrivals, it's very important. Yes, it's the first and the second important moment was very interesting and important for me, that you analyze it various method approximation. I can say it's my first example when I can look all these methods. I can say that some of these methods were development when I was as you, the youngest students. Yes, I had taught with Malavichka, and my teacher, Sergei Goldin. Do you know, yes, his book, Travel Time Inversion? No?
Sorry, if I
It's some book was published in the SEG series, the theoretical works. It's travel time inversion. Yes, in this book you can find yes the non-hyperbolic yes travel times and so on. Yes, different aspects before Malavichka. Yes, and it may be interesting with historic point for you. Yes, and after this analysis, I can better understand the modern situation with this approximation. Thank you for you, yes, for this analysis and for this work. And the next is an essential point was his analysis during the work, the features and the application of the two special type of norms, L1 and L2. Yes, this made it possible to reliability prove the following fact. It's the use phrase, the application of the norm showed to be important option to perform a good processing, presenting faster and more accurate result than the L2 norm. I can say that this is I can't say that this is a completely new result because early I can listen. Yes, the same results for the others, yes, researchers. But in your work, you repeat this some fact, maybe that difference this norm for the inverse problems travel time for the travel time. It's very important. I think it's 3 moments which will be interesting for me from your work. And now I want to go to my questions. Yes, one of these questions I discussed it with you now. It's that there's some analysis of the non-hyperbolic was in more early time than the Malavichka results. I can say that these aspects analyzed in seismology. It's absolutely. And now in the seismic investigation for the oil and gas industrials, yes, we back to these questions, maybe the more accurate. And for me, it was very interesting to look on this question through the new cycle. Yes, we know that our yes science development by cycles, and you presented the new aspect of this approximation approach because in our time we try to study approximation like some mathematics approach. So we can take the more order of the approximation, take the fourth order, and for the sixth order for the better approximation for the complex is travel times curve. But what was the interesting for me that you tried to take this approximation with some medium parameters. It's very interesting, but maybe you can understand, yes, in your the first discussion that it's not a solution of the inversion problem, because you used only approximation for the one travel time. Yes, curve, for like some reflection from the one boundary. But for the decision of the inverse problems and the estimation of the velocity model, you need to use few these travel time curves for the different boundaries. And now the modern approach using the different travel times curves and try to estimate the velocity approximation between these boundaries. It's a connection with the migration, yes, processing, and so on. So we need to use the tomography, seismic tomography task, yes, for this decision. So it's in your work, it's not a decision of the inverse problems. Yes, kinematic or yes, travel time inversion problems. You understand? It's the problem only approximation. Okay, but it's interesting because use approximation including some parameters of the medium. And it's maybe interesting for the future. I don't know yes now. Yes, and I can say the next moment that it was what is do you understand the difference between the asymmetry and the non-hyperbolity of the travel time curve? Is because for the conversion waves, you can have the asymmetry of the travel time curve. Yes, because you can look if you will have the CMP gathers, yes, when your analysis use yes a reflection wave, you can look asymmetry of the travel time curve, not a non-hyperbolity. Because why for the converted wave, very interesting the question about non-hyperbolity. Because the velocity for the S wave is the more slow than for the P wave. So for the big distance between sources and receiver, you will have the more hyperbolity of your travel time curve. Yes, for the complex wave. You understand? Yes, because it's a connection with the different velocity for the one part of the ray and for the other kind of the ray. And this given for you the more complex structure of our travel time curve. But in this task, you will have, yes, the two aspects, asymmetric, yes, and non-hyperbolity. Yes, please try to understand here the situation, because it's maybe important for the processing of the real data, and when we will have a selection of these waves and so on. Let's go to my real question. It was only the impression and some elements of the discussion, but I want to ask you about the why you write that only the complexity nature of the wave, or maybe the big distance between receiver and the sources can be given the non-hyperbolity. Because I can say that the complex and the curve lines of the boundaries given the same non-hyperbolity of the travel time curve. You understand?
Sorry, you mean about the generalization of the approximation when it's used the
No. I want to say about the complex structure of the model, because in your model you use only 1D models.
yeah.
Yes, for these models you can look only this aspect, connection with maybe the VTI anisotropy, or maybe yes the complex structure of the waves, the converted waves, yes, and or maybe yes, different distance and the influence on the non-hyperbolity. But for the 3D models with the curve lines of the curved surface of the reflectors, yes, you will have the non-hyperbolity in connection with these elements. I remember our some research in our lab connection with this question, because we need to use the more complex structure of the approximation for the travel time curve. Yes, if we will have the big curve lines of the boundaries of the reflectors. You understand? And I can look in your work, yes, some aspect of the studying of the pre-salt horizons, maybe connected with gas resources, or reservoirs, or oil reservoirs, and so on. Salt structure is very complex. So through this complex structure of the upper part of the stack, you will have some changing in your non-hyperbolic travel times. Yes, and I want to ask you, have you some maybe experiments connection with this influence curve lines of the boundaries on the non-hyperbolity of the travel times curve?
Well, you mean the relation with the analyzed being 1D? You mean the influence that the boundaries could be found in this kind of problem?
No. Yes, we and you show some your text when we told, maybe right, about the complex structure of the pre-solved results. But have you the same models in your researcher connection with the non-hyperbolic of the travel time curve?
The models, actually, they are from real data from Santos Bazin, from the press out from Santos Bazin. They are actually tested in two ways. One with the real information, and it was also modeled using few data of previous works, and also with few data found in the literature.
Yes, but why we did not use approximation for the real data, maybe for the real travel time curve? Yes.
Sorry, I didn't understand this one.
Let me say something. Professor Mitrofanov asked you about the. Do you have some examples of application of your approach to the case when you have not regular boundary but irregular boundary, which has
yes,
influences of a non-hyperbolic character of your travel time curve? Do you have or no? Something like that.
Oh, thank you. Yeah, I didn't test it. I didn't test for irregular boundaries. I was testing for only for multi-layered media, but with the with horizontal.
Nelson, you show me, yes, 1D model by your hands. I asked you about the curve surface. It's like the salt structure.
Yeah, I think that the application for future works is tested for irregular boundaries, maybe inclinated boundaries, and another kind of irregular structures. For the for the non-hyperbolic analysis, I think this was for now enough. I think it was interesting to compare the equations among each other, but I think for the automated picking, I think we should test in the future more different kinds of structures. Of course, inclinated structures or irregular structures. But I tested now for this kind of a little more simple structures to understand if the algorithm really can be applied. So we found it can be, and also for pre-salt models, they are the structures are very large. So the variation of the topography of a layer is not so strong. Of course, we can find this kind of variation, but essentially analyzing in a large scale, I think horizontal layers are acceptable approximation. But to analyze in a smaller scale, of course, you should try for different structures, irregular structures, inclinated layers, and anything we could imagine to find in this kind of geology.
Yes, but my question connection, I'm very interested in what you think on the next question. What non-hyperbolic effects are most difficult to deal with the level of approximation? What do you think? Yes. What is the more influence on the non-hyperbolic effects?
How the non-hyperbolic effects concerning how they influence the data, you mean? I'm sorry.
Yes, I can say that as I know, it is a VTI, yes, anisotropy, give a very big difference for the curve line for the big distance. Yes, you know, yes, this effect for the VTI anisotropy. But what do you think? If I will have the some velocity variation, maybe in layers on other kind, given the same big effects, connection with the non-hyperbolic.
Other effects maybe related to the complexity of the structure, you mean?
Yeah, yes, it's a connection with some aspect of the seismic tomography. Yes, the modern seismic tomography. When we try to given the seismic migration image of the medium, and if you have some variation of the velocity in a few layers, you will have the same effect non-hyperbolic or added, yes, variation of the travel time curve. You know this aspect.
Okay. If I understand, you mean the variation of the non-hyperbolic effects in a condition that we don't have only the same non-hyperbolicity. It's that's the example you're.
Okay. Did you look maybe on the result, some migration processing, or not?
For it could be used for to find the migration velocity, you mean?
Yes.
I didn't test for this specifically, but I think it can be adapted because their mass velocity should be different from the stacking velocity and therefore from the migration velocity, of course, right? So
yes.
But I think we well, I didn't test it here, but I think it's possible to apply, of course.
Oh, okay, Nelson. Yes, we can finish yes, this discussion. Yes, and I want to ask you about this some use phrase about the application of L norm showed to be important option to perform a good processing, presenting faster and more accurate result than the L2 norm. However, it can only be used with derived free optimization algorithm. And my question, why? Because if you will have the target function for the optimization and you show this is some function, I can use for the the same some processing, including derivatives, because I can estimate the some gradient of this function and use the methods which use the derivatives for the optimization strategy.
Yeah, but I found in many works about the application of L1 norm and the limitation of dealing with the of the L1 norm dealing with actually work together with derivative optimization algorithms is because the points that are calculated to be compared concerning the error cannot be cannot show a variation that can be described as a derivative of the. So if you have a straight line, you cannot describe this kind of variation analytically, right? So that's why I said that, because the other one norm couldn't be used with derivative-based optimization algorithms.
But you have no this program, because when we were working with optimization algorithm for the different norms, we can took some points. These points can given through the Monte Carlo method, yes, and after that we can use the some estimation of the derivatives, use the same strategy. Take the maximum of the derivatives, the direction of our optimization, tracing, and so on. What do you think about this?
Yeah, I agree, but I wasn't working specifically with the optimization algorithms. So this kind of application could be performed only if I adapt the optimization algorithms specifically. So that's why it could be done. It couldn't be done.
Oh, okay. So you have no yes some algorithm, yes. It's some package, yes, optimization. No, not use algorithm.
You mean the package of algorithms I used?
Yes, but my students the same. Take something program and use in his work.
Yeah.
Yes. Okay, I understand. Yes. How many iteration did you see in optimization? How many points you used?
It depended on the optimization algorithm, But for the two I suggested to be used at my conclusions, the F-main search that was proposed by is based on the another meat optimization algorithm. It used I think if I remember 104 or 140, around 140 iterations to get a very accurate result. But it can be used with less than 20 if you are not so if you don't need to get so hard with the optimization.
Yes. So you can look. Yes, you have so much points of your target function, and try maybe you use this is some derivatives. Yes, processing. Maybe it will be the more fast because your function, target function, is not so bad. But I want to ask you about, do you know the measuring function? Yes, if you have the some multi, yes, multi minimum function, you can use the some measuring function to have the some point estimate the global minimum. Do you know this strategy?
Calculating how it's called, calculate the measuring variation concerning to vary not only the calculated curve but the topology, you mean?
Yes, for example, you have many points of your target function, and use the some approximation through the paraboloid, for example. And after that, you very fast find the minimum of this paraboloid, and then use this point like the initial point for the next steps of optimization, because this point can be lie near of Earth's real minimum. You understand?
Yeah.
Yes, it's maybe the very good yes strategy for the multiple yes minimum function. Okay, this maybe this is some recommendation, because as I can look your function.
No, thank you.
Yes, maybe it's maybe useful for you. Yes, okay, I finished my question. I think maybe I want to discuss with you some perspective of the development, because I think it's very interesting approach that you development.
Thank you very
Yes, good luck in your work. Yes, but what do you think about extending your approach for the 2D data?
Yeah, it's what I am expecting to perform
Yes,
in future works.
yes, and how you will provide this research work? What some ideas maybe on this direction? Why I asked you? Because I can look on your equation which was presented like the Ghose approximation. And for this equation, you can change use x coordinate from the profile line to the square position. You understand? Yes, because it's the only the distance between sources and receivers. And in this case, you can have two coordinate x and y for this presentation, and in this case you will have 2D approximation.
Yeah, actually.
Yes, but I don't understand yet about the it will be enough or not, or maybe you need to change or rewrite your approximation, maybe, or maybe enough will be change the coordinate.
Yeah, or maybe applying it to in different dimensions maybe is a more simple way to apply it, maybe.
Yes, but maybe use parameters which used in the approximation. You need to change the same, because for the complex media, we will different changing of the parameter for the different direction. Yes, maybe, I don't know, but I think it's interesting, yes, question for me. Yes, yes, it's quite enough. It's only some ideas, because I think it's very interesting, yes, to development this approach for the 2D data.
Thank you.
Yes, thank you for your presentation.
Thank you very much. Are you satisfied with the answers?
What?
Are you satisfied with the answers?
Yes.
Thank you.
Okay. Thank you very much, Professor Mitrofanov, for your questions, comments, etc., etc. It's the comments of Professor Mitrofanov is very interesting because he represents he in our committee, in fact, geophysics, Russian geophysics of old formation. At almost 50, 60 years ago. I can say that Professor Mitrofanov, he was the first PhD student of Professor Sergei Goldin. Yeah. And so
Yes. Now
one comment. Okay.
Thank you.
Thank you. Now I would like to give words to Professor Jörg Schleicher from University of Unicamp from Brazil. Jürgen, por favor, please, your time. I am glad to see you.
Yes, it's nice to see you all. Thank you for the invitation. Thank you, Priimenko. It was a pleasure to be invited for this thesis defense. I really think, Nelson, that you have quite a content for your PhD thesis. You have done a lot of work and have lots of interesting results. On the other hand, and maybe that is also something you can already infer of from the observations and questions from the first two examiners in the committee, I think you need to improve your presentation. I don't think you do justice to your work you've done with the presentation you have chosen here. I think you will have some work to do to put this into a more readable shape. And in this sense, you will find several annotations on the version. I will send you the version with my annotations, the PDF, because I cannot imagine of mentioning all of them in the space, even if I would use the 1 hour that Priimenko told us that I would have. I could not make justice to all of them, and I don't intend to use the full hour. Okay. So I will more or less, I will project my annotated version of the thesis. I did the annotations in Portuguese because I think that's easier for you to understand what I'm trying to say. If it's not clear, then you still can always contact me and we can discuss what I'm trying to say here, what I'm trying to give you a hint in which direction to improve the presentation.
Okay, thank you.
And I will now more or less randomly open some of the annotations so to have an idea of what I'm talking about. So there will be remarks and observations, and there will be questions. The first question, actually, so let me start the presentation here of my version of the. It should replace yours now. Since the annotations are in Portuguese, I don't know whether they are really useful to the other members of the committee, but I will ask them in English, of course. So, but can you see it? It's working?
Yeah, I'm seeing it.
Okay, so this is on the title page. It's the first larger observation. If I open it, will it open on the projection? Doesn't seem to do so. Okay, then it's meaningless. Huh. You don't see I opened the projection that this box here is an annotation. I opened it and it doesn't show on the projection.
Yeah, not yet, unfortunately.
I think.
Sorry, okay, that might be true. Okay. Then I will have to make sure not to project the projection because then we get this infinity window, but yeah. I like to see what I'm projecting because then I see when the internet goes down or when my mouse is yeah. Okay, so let's see whether this is working. Here's the infinity window because HT is great. So the first observation here, it's very important that you make clear the concrete objectives of the work. And that's not 100% clear. I mean, you have this section where you state to do this and to do that. But for example, first question, all the approximations you use do really use the same number of independent parameters, which is still not clear to me after reading all of the work. Do they actually have exactly the same number of independent parameters that are to be estimated by the curve fitting?
Yes, the parameter posteriori parameters, yes. The last one, it used 5 parameters, not only 3 like the other. But the 2 exceedent parameters are for just to perform the adaptation of the approximation to the OBN condition. So you can obtain these parameters before performing the the main inversion.
Yeah, okay. There are so more or less a priori information that you have on the geometry.
Yeah.
Okay.
So these two parameters
Okay,
are partially
then I would suggest that you change the title of the thesis already to make that clear. Multiparametric is very not specific, very unspecific. So if they are all actually three parameters, with three parameters you mean T0, the
velocity,
hyperbolic velocity plus some non-hyperbolicity parameter, right?
Yeah, exactly.
So then I would suggest that you say this already here, that there are three parametric travel time, so 3-parameter travel time approximations.
Okay,
That is already clear that I mean, this probably already answers a question of Professor Ghose, that why some of the travel time approximations in the literature are not there, because they use more parameters.
Okay.
Okay, and then you still have to exclude the others that maybe also use 3 parameters in the text. I agree that that is an important question. You need to justify or explain at least why did you use the ones you used.
Okay.
The next question is, if you are interested only in finding the best travel time approximation, or are the parameters that you find by adjusting those travel times are of any interest to you? Not clear. Even after reading the text completely, to me, it seems that you're not interested in the values of the parameters themselves, but only in fitting the travel time.
Yeah, to fit the travel time and targeting to obtain the best velocity. So the boundaries I used are to perform a better inversion, to aim to obtain the velocity closest to the reality. However, of course, the third parameter is not the as it's not the focus. It's just it's just to perform a better curve fitting for the velocity, aiming to.
So the third parameter is basically to absorb the error from the deviation from the hyperbolic event, so that the V actually describes the hyperbolic part, and you get a better estimate of the RMS velocity.
Exactly.
Okay, then this needs to be made clear in the introduction, that is your aim. No? And maybe you can, as a perspective, also indicate that future use of the second parameter could be some tomographic inversion. So even if it has no clear physical meaning, because that's not your objective, it's still a parameter that describes the travel time. And if it describes the travel time better, then you have more information about something. And a possible use of that parameter in the future could be some tomographic inversion to derive actual physical parameters from it also.
Yeah, for now, the difficult for me is just to understand what exactly. Actually, it represents all the events, not hyperbolic, but it's hard to determine what exactly we have when we recover this information. So, the event is not this kind of no hyperbolic, but what does it mean? For me, it's just a little.
Yeah, I mean that you can post a gauge to some later stage when you say, okay, I just now want it to absorb the non-hyperbolicity for the velocity to become closer to some theoretical value that I want to estimate. And so then, of course, anyway, you would need to show that this velocity estimate improves in quality, that you really gain something. That's also something that's missing. You don't evaluate the quality of the RMS velocity that you estimate by the fit. You show that the fit is better, and that's all. So the objective is to get a better estimate of the velocity parameter. So you need to show that you're doing that.
Okay.
And if you get a unimodal travel time function with a perfect fit, with completely wrong parameters that have no physical meaning at all, then what's the use of it? If you want to estimate velocity, then you have to show that the velocity parameter is actually at the value that you want to estimate, or very close to. Okay. The other possibility is to say, okay, I have two parameters that I can estimate, and the physical meaning, I don't care about any of them, and I leave it to a later processing stage of maybe inverting them, both of them, in a tomographic process. But you just said that the velocity is one of your objectives. So then I would think that you should discuss the quality of the estimated velocities.
Okay.
But anyway, you need to make these objectives very clear from the beginning. Also, the models. It is not clear in the beginning that your models are 1D.
Okay. Sure.
You should state that at an early stage. Maybe you will see that some of my remarks are redundant or even contradictory, which comes from some kind of this, that I recognize something that you actually state at some place in the thesis that I needed earlier. So I had a question at some early place of something that maybe was explained later on, or explained it in a way that makes the question in fact obsolete or even contradictory. That can happen. Sometimes I also jumped from the beginning to the end and back to the beginning. So I might have put in earlier places already questions that make use of something said later. I need to go from the basics, from the hypothesis to the results, and you have to make that structure very, very clear.
Okay.
So now let me go, and I here, this is red because I think this part of the abstract is too detailed for an abstract. I think it can go or reduced at least to a single sentence or so.
Okay.
An abstract is supposed to contain your contribution, what you did and what you conclude. Okay, and you need to do the introduction to the topic, to the introduction. The abstract is supposed to be for a reader who knows about the problem and wants to know what you did. It doesn't need an introduction. Okay.
Okay.
This one here says that you should
Okay.
you should put the information on what you found. You should remember always that the abstract is what you want the reader to remember from reading your work after 5 to 10 years. Still, okay, that is the work the guy who did this and that. He found this and that. Okay, so what you want the reader to know about your work after quite a while is the information that should be present in the abstract. As I said here, it's a synapse. It's not a trailer.
Okay.
It's not meant to make the reader curious. It's meant to give him the information. What is the most important information contribution of your work? That should be there.
Okay.
No. The list of tables and content. You also need to improve the English a little bit. So the yellow markings generally refer to some observations, maybe in the introduction, mainly to the English. The darker ones are generally some questions.
Mm-hmm.
So let me open this one. Okay, oh, I don't agree with this. So what did you say here?
Motion waves.
You say that the S waves are only recorded if you do multiple components.
Wait, sorry. Well, I put my entire screen again because it's not finding the window with the. Can you see it now? So can we proceed?
Okay.
What? His screen was freeze for me. Yeah, the microphone is on, but it's not online, I think.
Let's wait it.
Richard? Voltou?
Eu estava achando que eu não tinha mais nenhum feedback, então agora olhei e tinha aqui, o Google estava me perguntando para dar permissão novamente, só que estava atrás do meu PDF, então eu não tinha. Então não sei quando foi pedido. Vocês não escutaram mais nada, então.
Isso.
Ah, isso não vi. Ah, isso deve ter cortado a minha. Ah, então aí você provavelmente cortou aqui a minha conexão e eu nem percebi nada, não escutei nada disso. Então vamos voltar para aquela etapa. Eu não parei, nunca parei meu compartilhamento. Se alguém colocou outro compartilhamento, ele tira o meu. Então, se o Nelson tentou apresentar alguma coisa, ele tirou o meu. Ou talvez tenha caído brevemente minha conexão.
Eu acho que foi a conexão que caiu. Porque o meu já estava apresentando desde antes.
Uhum.
Aí acho que caiu a conexão e aí interrompeu o compartilhamento.
Caiu a conexão mesmo.
Estava começando a falar da introdução.
Estávamos na introdução?
Isso.
Então, deixa eu voltar para lá. Vou apresentar agora. É por isso que eu gosto de ver o que eu estou apresentando. Eu já tinha falado, estava falando sobre isso ou foi antes ainda?
Não, estava falando sobre... Você ia começar a falar sobre essa parte em laranja.
Ah, tá. Mas você estava querendo me mostrar alguma coisa, é isso?
Não, a transmissão ainda estava.
Tá. Então eu vou ver se eu consigo manter a janela um pouquinho visível para mim, para evitar que eu não perceba quando isso acontecer. Pronto. Ok. I see the screen now. You see this the calculus PDF, which I use for my class. Okay, so then let's go back to this part, which I was just commenting that this is an affirmation. I think it's precise. It's not that you don't have S waves present in single component recordings. You use multi-component recordings to get the polarization out of it. So you know which event is a P wave and which event is an S wave, because that information is lost if you have only a single component, because you cannot measure polarizations.
Yeah.
So I think you need to reformulate this.
Okay.
And I started talking about the introduction, saying that the other things here is mainly English ideas of maybe how to improve a little bit the writing of the English here. Okay, so that's why I want to talk about these yellow ones in the introduction.
Okay.
And this is general. Yellow are more remarks, and the dark yellow, the orange ones are the questions, and this red one is just to say that I stopped editing the English here because I had to go.
E caiu de novo.
It's for me. Georgi, yes, okay. Oh, okay, I understand.
This is another Georgi.
Caiu mesmo, porque tá congelada a tela e ele não, o microfone não mexendo.
Unfortunately, with our internet, sometimes we have such kind of problems. Yeah.
If I may just say something, that the president of the committee or chairman of the committee, Professor Priimenko, is it not that you take a decision here, because we are pretty much wasting our time on digital. I mean, we are used to using digital medium for long time, but it seems like we are pretty much lost here. And also it is almost like correction of the PhD thesis going on. So if it is a defense, then we stay. And if it is a correction session, then we just come back after some time, or what would you prefer as chairman of the session?
I don't know. I have no opinion. Let's speak with another member of our committee, Professor Renato. What do you mean?
I'm not sure, but I think you have to finish all the process now. We don't. It's not allowed to interrupt and then continue in another time on other day. So unfortunately, I think I have to complete all the process.
Yeah, I think so. Yeah.
Okay.
I think it's better. Yeah. Let's wait a little.
I'm guessing if the problem with there is a problem with the connection of the Jorg, and if he doesn't share his screen, maybe it would be better. I don't know. And then Nelson open the screen and instead of Professor Jorg, I don't know.
Is that
Mm-hmm.
Here I'm back.
Okay.
Yeah, I had to work outside my office in my home today because we had 3 internet users at the same time. My son has school online and
Yeah.
my wife had classes to give, so I went to a different place where the internet is a little worse, but I had solved that this morning.
Mm-hmm.
I had a good connection until now. But since the office is now free again, so here's the connection certainly better.
Yeah. Okay. Let's proceed.
So let's go back to where we were.
George.
Yes.
Alguém? Issue.
Something froze on my screen. I will need to disconnect and connect again. The window has frozen. Yeah, but I'm not at the side of the router, so this is no problem anymore. I just have a problem that my screen has frozen. So I might need to, don't know whether the problem is this, can't even switch the workspace. So I might need to reboot the computer now. I don't know what it makes the computer screen freeze. I tried to share the screen. I clicked on allow and then the screen froze completely. I can move the mouse. At the moment, I cannot do anything because literally my computer screen is frozen. I cannot even switch the windows and nothing. It's completely frozen. The mouse is moving, but I cannot click on anything with any effect. So I can't. Yeah, I can't even switch.
Yeah. Mm-hmm.
No.
No.
Yes, I am.
We
at the
have
last one.
next Professor Renato. Yeah. After George. Yeah. Mm-hmm. I think so, but let's wait a little, George, to turn and to speak with him about this change. Mm-hmm. Okay. Yes, exactly. Okay.
Sorry. Okay, here I'm back again. I had to kill the Firefox completely, the application. And then mas eu estou logado como outro usuário. Eu vou entrar com outro usuário. Sem problema? Até breve.
Okay. Oof. So digital war, unfortunately.
Okay, here we are.
Okay.
Once more. No. Oh my. Okay. Yeah, I don't think that the reason was the camera. I think there was a problem with Firefox. And now it even knocked down my desktop switcher. So, but I think that with Chrome, this thing should be solved. If we face trouble again, I switch off my camera. I mean, I can switch off my camera. We don't need it if I'm projecting. Okay, here. Here we are.
Okay.
Okay?
Okay, let's go.
Can you hear me?
Yes.
Okay, great. Then here we are. I was just saying that this red mark is just to say that I stopped working on English here because this was taking too much time. I would not have been able to read the contents of the thesis if I had continued with the English corrections.
Okay.
Okay, and here my suggestion is to remove the section 2.1. I don't think that on a PhD level anybody wouldn't know what compressional and shear waves are. I think there's no need to put this in. This is the same observation as before, and then we go to here. So this was also not heard. Am I still online?
Yeah.
Yes. I will ask this now once in a while because if I don't hear you, I'm not sure anymore. Okay. So the suggestion here is to change the order of presentation, to put the derivation of your approximation first, to clearly state the hypotheses that you're making to do the derivations. This has two advantages. First, you will have all the variables already defined when you state the other travel time approximations. Now you're putting the variables and explain them, and then later on you reintroduce them again in your derivation. And the second advantage is that you will have your travel time and then the others very close to each other. At the present, in the present form of presentation, you have first the other travel times, and then a huge part of derivation, and then comes finally your travel time approximation, which makes it hard to compare them when you come back from the numericals and want to see what's the equation again, and then you have trouble finding them in thesis. If they're closer together, then that's easier.
Right.
So that's my suggestion here, to switch the order of presentation. Yeah, okay. Here I would ask you to put in the relationship to the Thomson parameters. You say that the S parameter here depends on the Thomson parameters, but you don't give the relationship. Since in the other cases you gave it, at least partly, so that seems to be somewhat asymmetrical. So I would expect to have the relationship in terms of the Thomson's parameters here too.
Okay.
Here is just a misprint. I think the x square belongs in the outer in the outer square root.
That's correct.
What is this? This is just an x which is not in the mathematical style. Just
okay.
Nothing. Yeah, here I had difficulties understanding the definition of the variables because it's very short. And then later on it becomes clear when you do your derivations. So this will be an automatic benefit of switching the order.
Okay.
This proper value of x over z is not clear what you are wanting to say. Would you explain this, please?
Is the relation between the offset and the depth.
Yeah, but depth doesn't really appear in your function, and offset is movable. Offset should go from 0 to whatever offset you have. So what is the meaning of a proper value of offset over depth in this context?
No, it's related to the RMS velocity, because the Liu one approximation is more well used for under this relation, under this value of this relation. So
okay, so it's the more or less the validity region. Your approximation is valid up to that offset.
Yeah, exactly.
Which is defined in a relationship to depth. Okay, so this needs to be improved here. It's not clear what you mean by proper value. You need to say that. Okay. Here is the first hint that you're speaking about media with only vertical velocity variation. When we are already inside the 3.1, after all the presentations of the equations, here you say that P is constant along the ray, which is only true if you are speaking about a V of Z medium. But you didn't state that hypothesis. So that's why I said when you put this first, then the order is more natural, and you can put all your hypotheses before starting the derivations. Okay?
Okay.
So when I read this first, this was my question. Why are you saying this? This is not true in general media. Okay, but later on, of course, then you see, I saw that your hypothesis is a V of Z medium.
Okay.
Okay, here is x squared, nothing of importance. Huh? You will just have to fix that.
Okay.
And what is here? Yeah, I found this very long, this derivation. You might consider moving part of it. I'm not sure whether my suggestion, the part between equations 26 and 49 is the right choice, but maybe you can move part of this derivation into an appendix to make it easier for the reader to access your result and your proposed equation. It's a very long read to get at your equation here.
Mm-hmm.
So maybe you can just, that's more like a suggestion. You evaluate whether there is maybe a part of an auxiliary equation that you can derive in an appendix and come faster to your equation.
Okay.
Yeah, here again we have a problem with the hypotheses. I mean, you are citing here in the context of an anisotropic medium a parameter that was defined in the context of an isotropic medium. So I think you need to make sure to be very clear and specific of which formula applies to which situation, or if you can generalize isotropic parameters to remain valid in anisotropic media, or what are again hypotheses here, citing an equation from an isotropic relationship and using it without any further explanations in an anisotropic setting is not sufficient for a reader to understand what you're saying.
Mm-hmm.
So you need to make that clear. Okay, you didn't define the delta t's and that appear here. Of course, it's more or less implicit, but it's bad style to use variables and hoping that the reader will understand what they are meaning. Okay.
Mm-hmm. Okay.
E aqui em algum momento, from this point on or a little later, I started not to be able to follow your deductions.
Mm.
So I had to stop trying to understand each step.
Yeah, try to explain.
So I think you might need, and again, maybe in an appendix, how do you get from equation 22 together with these to this equation? Because there's no VC whatsoever in the equations you cite here. And then now here appears a VC2 without being present in the equations that you say you use to derive this one. So this is hard to follow. So maybe there's just some equation missing that is more or less obvious, but I didn't see it. But I couldn't follow it. Okay.
Okay.
So maybe it's again a case for appendix, part of the deduction in an appendix, and I leave that to your criterion. I just told you where I had difficulties here too.
Mm-hmm.
The deductions. Okay. Yeah. This is VTI, right?
Yeah.
You never mentioned that explicitly. You say isotropic and anisotropic. It's again this question which is recurrent in your text, that you need to state your hypothesis.
Mm-hmm.
This is a larger one. You didn't explain the meaning of the index I in equations 50 and 51.
Okay.
So this is what, layer?
Yeah, it should be the layer.
But then you want global travel times, not layer travel times, because this is the formulas that enter into the sums. Okay, okay.
Yeah.
But then still, if I put this sigma y, sigma I here, then the del epsilon minus delta appears like it is here, and the rest of the equations are identical. So I get already the relationship that these two are equal, except for this factor of gamma 0 squared. When you say it's sigma, it's gamma effective squared, not gamma 0, and also it's only after some approximation.
Mm-hmm.
This also confounded me here. Because it looks to me that when I put this in here, those two are basically the same. So maybe there's some misprint here in some of the formula. Because you say only after neglecting this guy here, you get a similarity. Okay, you check that and explain it maybe a little bit better.
Okay.
Okay. Yeah, this question here is about exactly where is the part starting that you did, which is the part of the derivations that is still literature. Somebody else or somebody, one or more papers did come part of these derivations, and where does the part start where you actually derive your proposed formula?
Mm-hmm.
So this is not clear.
Okay.
Which is where starts your contribution. Obviously, somewhere you start to do your own derivations because you end up with a proper proposition for an approximation. But I could not identify the point where you stop using what other people did and do your own stuff. It seemed to be, it might be here.
Yeah, it's there exactly. So I'll make it more clear.
Okay, and this equation, at first I thought this doesn't make any sense because you don't tell me what the coefficients are. Only that there is a relationship between C3 and the other two. And then you say you have this equation, but you must derive the coefficients.
Yeah.
So I guess that it is something like a candidate solution. You want it to have this shape. Shouldn't I? By the way, shouldn't this be x4? No, I don't know. Because in the travel time, the one in the numerator here in this term is always x4. X to the fourth. So maybe this will need to be checked. Maybe there may be a misprint.
Okay, I'll check it.
So if xp is xc and you haven't defined xp, then is there a need to have two variables with the same meaning?
First consideration.
Is xp just a new name for the horizontal coordinate of the conversion point?
Sorry, let me check the consideration. And there is a solution to the. Yeah, it's actually the same of C. How can I explain? It's not just changing of the name of the variable, but it's considering it was considering the incident P wave as the different from the incident P wave in the conversion point. It was considering and not the the XP was related to the incident P incident the conversion point and not considering the CMP. That's what I'm trying to say. That and then I start to call it XC because we start to work with the conversion point. Is that
XC was defined to the latest here, but I think it was even earlier defined. XP wasn't defined as far as I remembered here. So if you want to make the observation that these two distances are actually the same, then they both need to be defined first.
Okay.
Yeah, exactly.
And then here you state that XP is an odd function of X without any explanation. XP is part of X. XP is the part of the P wave that's covered in the horizontal direction as far as I understood. So could you do an argument why XP is an odd function of X?
Sorry, I think the microphone was cut.
Yeah. Again, connection problems. I was asking here if you could give an argument why XP is an odd function of X. For me, XP is some fraction of X, which depends on the velocity ratio. Yes.
Yes.
Why would it be an odd function of X? You use it to justify why you only need odd terms in the Taylor expansion, but I think you need some physical justification why this is true.
Mm-hmm. Yeah, because I was using the XP as the considering the incidence in the conversion point, and the X considering the incidence for a conventional event, but it's not well explained. That's the problem. I think I need to describe it a little better.
Yeah. Yeah, I couldn't also understand this equation 60, because when I put this limit x to 0 here, then I just get 0, unless the coefficients go to infinity, which I don't think would make much sense. So this equation would say that the conversion point is 0.
This part of trying to describe that the conversion point relating the incident P wave and the reflected S wave. So I'm trying to say that if the limit goes to infinity, the zero is the distance between the incident P wave and the reflected S wave gets close to zero, because the distance among them.
Yeah,
Sorry?
but you want to discuss the coefficients, and what I'm guessing, also from equation 62, I wrote it in this observation here, is that the limit should be on this equation, not on this one. I think that the XP is the sum of the odd exponents of x with some coefficients, and the coefficients are obtained from the limit of this derivative when x tends to 0, because it should be taken the derivative at 0 from the Taylor expansion. So I guess this limit just belongs here, because here it wouldn't make sense. And here I think it's missing, because if you look then at the case where k is 0, then there appears a limit which wasn't present here. So from the combination of equations, I would guess that this limit should be here and not here. Also, is there a meaning in changing the order of the index here from 2k to k2, or is this just a digitation question? Because if it's just, of course, 2 times k is the same as k times 2, but if there is no need, no significance, then this is something that should be avoided, because this is details who confuse the reader.
Okay.
Because once you do something like that, the reader asks himself whether there is a meaning to it.
Okay, I'll check it.
Okay, I guess here is the application incorrect. I think it should be only one.
Yeah.
In contrast, I think here is maybe some second UPI missing. I'm not sure. So in summary, with this all these doubts, I had to finally really stop trying to follow the deduction here. It was getting too much to try to infer which are the misprints and which are the actual meanings of the equation. So I think you need to improve that, so that one can follow this deduction here, this derivation.
Yeah,
I
to
really,
make it more clear. Yeah.
I really spent quite some time in trying to understand, which I could tell that this should be only a single UP, and probably here there's this guy is missing, so probably it's just happened that you wanted to insert it here and ended up typing it into the wrong equation maybe. But you see, if I as a reader have to try and go into this detail of interpretation, then it's impossible to go on and try to understand the equations. Okay, so I would really ask you to do a thorough revision of this deduction and this derivation, and make sure that these equations make sense and express what you are trying to express. So then there are no annotations anymore in the rest of the derivation here, because, as I said, I stopped, and then restarting at some point doesn't make sense. So I jumped to the final expression of your travel time, which is quite some time below. Okay, so you say here 5 parameters, 3 parameters to be recovered. But that's not actually the case, because you don't ever recover T0. You do the recovery for a given T0 or for a set of T0s. So you need to be also a little bit more careful about this formulation. This got me confused. This actually got me confused as to how many parameters you really have and if it's comparable. That's why I did ask that question as the very first question in the beginning here.
Okay. Now, just I performed the inversion for the 3 parameters, for T0, V, and the third parameter. But the forward problem with the topological analysis I made with the as the way you said, with in a set of T0s you consider the so it was just to test the limits of the quality of the equations for during the inversion. But it's of course it's performed only for the velocity and the third parameter.
Yeah, but I think T0 is not a fitting parameter like the other two. T0 is just that you do that analysis for every T0, and then you get a value for the other two as a function of T0. For each T0, you will get a pair of 2 parameters.
Mm-hmm.
That's also why in your numerical analysis, you always have a 2-dimensional picture of the objective function.
Mm-hmm.
Because those two are the parameters. Okay, I guess, and this was the same in your presentation. I think these indices 1, they should be i's.
Oh yeah, sure. You're right. You're right.
Should be the summation index here, right?
Yeah, it should be i's.
And I think it would be more easier would be easier for the reader if they would repeat here, so that to make clear that what you're putting here as R, which is not defined, that this is the definition of R, which is nothing else but exactly the argument of the sum here.
Mm-hmm.
So I think you should repeat the indices. Yeah, this distortion into a semi-Gaussian wavelet. Well, actually, I don't think it's a distortion into a semi-Gaussian wavelet. It's a phase shift. It's a phase rotation from the
real wavelet, you know.
From the real part into the imaginary part of an analytical signal.
Mm-hmm.
So,
yeah, the word distortion is not the best option to use here. No,
distortion is okay. The problem is that I did this graph here. The blue one is the semi-Gaussian wave, what you call semi-Gaussian wave. I hadn't heard that. It's the integral of the Ricker wavelet, or the derivative of the Gaussian pulse.
Yeah.
And actually, what you see is not the blue one; it's the green one. The green one is the Hilbert transform of the Ricker wavelet.
Of the Ricker wavelet, yes.
That is a 90-degree phase rotation of the Ricker wavelet. If you put it into the frequency domain and multiply it by I to the minus IP over 2 and transform it back, then the Ricker wavelet will take this shape. That's because the reflection coefficient gets complex when you pass the critical angle.
Yeah.
And that makes this phase shift happen. So it's actually not the blue curve that the wavelet is turning into, it's the green curve, which look pretty similar, except they have different scale. I've put them here into the same scale. Actually, the Hilbert transform is smaller than the derivative. I normalized them with the same amplitude here.
Oh.
But the shape is very similar. So with a little bit of noise, when you don't see these small side lobes, you can think one would be the other. They are pretty similar. They have the same extension. They have pretty much the same shape, but actually it's not the derivative or the integral of the Ricker. It's the Hilbert transform that you're seeing. Okay, so this needs to be improved. Yeah, here you're citing figures that are in the appendix. I don't think that is a good style.
Okay.
I think you should put the figures that you cite in the text.
Okay.
Okay, here I've understood definitely that you're restricting all your tests to models that vary only in depth, and this is way too late. Okay, so this is why I told you already before. You need to state that in the very beginning. Okay, here I had to go back and forth.
The microphone is failing.
Between the figure and this would be really nice if you could put the PP, the BP velocity profile here. Immediately associate bending with a strong and this worrying. So, oops. Okay, ma sto di volta. Estamos de volta. Okay. I was asking you to put the velocity profile of the associated velocity. So this is the P reflection. So this is associated with this velocity profile. If I had this here, then it was much easier to associate the behavior of the ray with the velocity profile. I had to do this to understand what's going on with these rays and find out that this here happens probably at this. No, the first larger contrast is a little below 2000. So this is the largest contrast, and this strong bending is the top of this reservoir zone, and this bending to the bottom is the lower part. But it was a bit uncomfortable to associate this behavior with the profile. So if I had the profile here, this would be much easier. If you could put it into the same scale and have it to the side of the rays. And here, of course, we would need both profiles, the P profile on the one side for this side and the S profile on the other side. It's funny that the S ray is not bending at all, in spite of having as strong contrasts as the P side.
Actually, it is because of the scale, but it's bending a little, but much less than the.
Yeah, I see some bending, but I don't see, for example, this strong bending of the decreasing velocity. I mean, there is a decrease in velocity at of being lower velocities, I would expect a similar behavior, because the behavior of the angles between the ray segments is just the velocity contrasts. It's not the absolute values. If you put 1/3 of these velocities in and trace the rays, you will get the same rays. So this is really a very strange behavior here. I didn't understand that.
No, but this is just because they scale. It's not the variation. The inclinations are proportional to the others, but it looks like that's more much more banded due to the scale is to make everything appear in this side of figure.
Okay. And then what is this? Okay, this question was already asked before, whether you used pre-existing programs or whether you did the implementation, is an important information. It's not critical in any sense. You can do either, but you need to tell.
Mm-hmm. Okay.
Okay, this is smaller things. I didn't understand this figure and want to say with it. So I think you need or to explain it better or remove it. But if it's only peripheral to your explanations, then maybe you can decide just to remove it. Or if you leave it in, then you need to explain a little bit better what are these lines? What are you trying to say here?
Okay.
You have no meaning of the x-axis or the y-axis and the circle and the square. They don't represent anything to somebody who hasn't seen that figure maybe in some other publication earlier. I didn't, so I couldn't make sense of it.
Okay.
Okay, now here in this figure, you say that red dispersions represent the global minimum. I don't know what you mean by dispersion in this context.
Yeah, because this point is a set of points. Because I
okay.
all of the inversions. So if I
Okay.
make a zoom in the MATLAB, you can see hundreds of points, hundreds of dots.
Okay, maybe you should then. Maybe I missed that explanation somewhere in the text, but I didn't see it and I couldn't understand it. So maybe you need to make that clear in the text somewhere.
Okay.
Yeah.
And instead of complexity, I would use the word shape here. I think the word shape is clearer regarding what you're doing. Complexity has a mathematical meaning, and it's not what you're wanting to say.
Okay.
And yeah, this is maybe needs a little reformulation, but this is the point. What I'm making here in this box is regarding the values of the parameters. You're saying that your model converged here. Actually, you don't have blue points in this figure, right? Or didn't I see them?
Yeah.
So I would suggest to remove the part of the sentence regarding to blue points when there are no blue points.
Okay, sure.
Because I hunted blue points here and thought maybe they're in the black part, so I can't see them. So I think you should mention blue points in the caption only when there are blue points in the figure.
Okay.
And but maybe you should at least give a hint of what velocity value you are expecting, maybe a green point.
Okay.
If you also know which value of the additional parameter is the one that you are expecting that should be found, then you could put in some green point at the ideal value where your algorithm, where you would your algorithm like to end up. No? But then this is again physical meaning of the parameters. You said that the additional parameter actually has no physical meaning. It's just to describe the analyticity to make the estimate of the velocity better. But then you should at least at the vertical axis here with a green dash or so indicate which is the velocity value that you want the algorithm to find.
Yeah, maybe a green arrow to indicate
that this guy is at a position that is interesting or not.
Okay.
Okay, because I mean, if I look at the other equations, they have other shapes, and the minimum point moves to another place. I think in the same model. I'm not sure. This is model 1. So we have here PPS, Marchenko, and then we come to Al-Khalifa, and you see the minimum is at a different point.
Yeah.
The velocity here is 2,780 or something like that. The velocity here is more than 2,900.
Mm-hmm.
So this is the same model, the same reflector. So the velocity should be 1. So one of them at most can be giving a realistic velocity value. So I think that should also be a criterion. If that is your objective, to improve the estimate of the velocity value, and that should also be a criterion in the evaluation of the formula.
Mm-hmm.
Okay.
Okay.
So maybe you come to another conclusion regarding the quality of the non-hyperbolic approximation, because even though you can't fit the velocity as good, maybe the parameter is better. Because actually what is important for the inversion is the velocity parameter. If the velocity fit is not as, the travel time fit is not as good, and you have a little more residual error after the optimization, but the minimum is at a good position, that is physically more meaningful.
Mm-hmm. Yeah, no, sure.
And here it's 2,100. So these positions of the this is the velocity aspect velocity. Okay, so this I need to compare with this one. Okay, this is closer, but still it's a V of Z medium. You can calculate the true RMS velocity to that depth for which reflection event you're doing this analysis. Actually, I don't think I saw which reflection event are you referring to? The top of the reservoir, I guess.
Yeah, exactly.
Okay,
Please,
so
may I comment, please? Sorry to say, but Professor Priimenko, we're reaching almost the limit of the section. I ask you.
Yeah. Okay. As I said, I won't be able to put all my questions here. You will see them. Take them as a guide to help you improve the presentation. As I said, I think you have really contents that are worth a PhD thesis, but you need to improve the presentation, and you have to have a red line through the text stating what your objectives are in the beginning, and then in the conclusion mentioning them again and saying why you have achieved them, or what kept you from doing so, and also some hints on what are the next steps in this research. Some future work should be mentioned in the conclusion section. There is nothing like that. Okay,
Okay,
I think I have made my main points and questions. So, thank you.
Okay. Professor Jorgen, many thanks for your valuable observation, comments, and suggestions. As I can, I could say that all the suggestions will be used to improve the final version of the thesis. And now I would like to give words to Professor Renato Luiz Prado from University of São Paulo.
Okay.
Renato, please.
Oh, thank you, Professor Priimenko. First of all, I thank you, Professor Priimenko, for inviting me to take part of the defense committee. I'll be brief in my comments, I promise. I start with a general evaluation of your thesis, Nelson. You propose to study and investigate an interesting problem, the non-hyperbolic approximation for converted waves in OBN acquisition, which is a very interesting topic to study. Even as mentioned by Professor Ranajit, this is not a new topic of research, but you define some objectives and analyze the results under different interesting aspects. Different approximation equations, including your own proposition, test the different optimization algorithms, use norms L1 and L2, and 5 different geological models, 3 for pre-salt and 2 post-salt. You develop these subjects in a good way, and you got good results in my evaluation. You've done a lot of work, no doubt. A criticism that I detest is that as you generate a lot of graphs, you describe each one in a lot of pages that for me was a little bit tiring and difficult to follow sometimes. But to conclude this general comment, I enjoyed the reading and I learned a lot reading it. Well, besides the fact that I'm not an expert on mathematical geophysics, I was perceived by the specialists, colleagues who have already covered the main aspects of your thesis. So I don't have too much to add. So Nelson, I have just a few questions to ask you. First one is regarding the geological models you employed. You didn't make any reference about the criteria adopted to create these models. You mentioned that you extract information from well profilings, right? But I missed some contextualization of the geology in order we have the comprehension how these models are realistic or credible. Why you do not extend a little bit more about the geology or not give more reference? This is one, but another one to you answer together. And about the OBN array model that you consider, I mean the distance between the nodes, the minimum and maximum offsets. These are the standard configuration employed in the oil industry. I don't know. I ask this because the big offset distance is one of the reasons of the non-hyperbolic behavior of the travel time curve. And even if this is a standard configuration, why you do not limit your analysis to the maximum offset of around, let's say, 5,000 meters, which is the depth you consider for the interface. And but you analyze in much far distance offsets.
Oh, sure. Thank you, Professor. And well, first about the first question. I really need to describe a little more about the geology, of of course, I think it was just a simplification of the contest, but I think it would be much more interesting if I describe a little better the region. And about the offsets, I think the problem actually is, well, of course, the RMS velocity will be much more different once we have 10, 12, 15 kilometers of the maximum offset. So for this analysis, I chose larger offsets than the usual, because of the just to try to perform the tests in a harder condition. So if the analysis could be performed for more than 10 kilometers, or more than 8, 9, 10 kilometers, that is the usual sun acquisitions are performed. Trying to do for more than these limits, I think the tests and the equations could be tested in a harder condition, and then if it works for this for a condition with this kind of difficulty, we can use it for more realistic difficulty in this case. And essentially many receivers were used essentially to test the automated peak. So that's why I chose so many receivers and so large maximum offset, because if it could get the target reflection for more than 10 kilometers offset, it's easier to obtain this information for shorter offsets.
Okay. You agree that it doesn't make sense to analyze in the figures that you analyze the errors in the time travel for distance for the hyperbola in offsets more than 5,000. It doesn't make sense of course, even the Dix equation is not
oh yeah,
to make this analysis. Okay, but it's okay. In the page 44, you mentioned, I have here the asymmetry reflection seismic event is generated by the difference between the datum of the source on the ocean surface and the receivers on the seabed. I just was thinking this could not be solved employing a kind of static correction before to imply the approximation equations you studied. I don't know if this makes sense, this question, but you corrected the thickness of the water layer, so you can make like static corrections to remove this effect and then analyze the curves, the hyperbolicity.
It can be, but it's easier to perform this kind of analysis than performing a statistical correction, because you don't know exactly the depth of the sea bottom, and you have the variation of the water surface. So that's why it's more used than a statistical correction.
Okay. Another question is in page 80, you describe the automatic picking using spectral recomposition that you employed in order to perform the velocity analysis. So, if I understood, you generate the synthetic seismograms that you show in Appendix A, and then apply the spectral recomposition method to pick the reflection times.
Yeah.
It would not be possible to employ like a semblance analysis, a coherence analysis, incorporating the different approximation equations using directly the synthetic seismograms. Another doubt that came to me with your presentation today, this method didn't work for long offsets. Is it correct? I think you mentioned it. What was the average maximum offset that you see that works? It works.
You mean the automated picking?
Yes, using this spectral recomposition.
Actually, it wasn't working for large offsets, only for the model number 4 and number 5, which are the models, the post-South models. And it happened because of the difference of because of the distance of the structures. Once we have the carbonate reservoir, the sandstone reservoir and the shale sealing layer. And then we have other sandstone structures above them. And because of this, the similarities of the shape of the wave of the phase and the other wave parameters, it makes much harder to separate the information of different signals from different interfaces. That's why it works very well for the pre-South, because we have 2 kilometers of South, which presents a very different set of physical properties than the carbonate reservoir. So we have not only the big distance separating them, and therefore a big difference in time separating them, but also a strong variation concerning the spectrum. So that's why we can find, because the amplitude, the frequency, and the phase varies in a much different way in the South if you compare to carbonate or sandstone or other kind of structures.
And about this, because I was figuring out not use a classical technique for velocity analysis, like a semblance, for instance. You can use it directly in a real seismogram, because you comment that you have before to implement this technique to make some mute areas in order to get the process more fast and more exactly, but it's possible to implement this kind of approximation in order to analyze the coherence in like a function like semblance to this kind of approximation.
You can use it to calibrate a semblance analysis. Of course, this one, the automated pick, with these constraints I determined here, I could get only the top of the reservoir reflection. Of course, the semblance analysis we can obtain the information of the other layers, but we can analyze 2 points. because the semblance, you have more garbage in and garbage out involved, because you have more human influence in a semblance analysis. This one, with the analysis I'm proposing here, we extirpate absolutely the any kind of human error, because it's all performed in an automated way. So that's the first point. So we can use to calibrate the semblance for the last layer, for the target layer, and then with the calibration of the semblance, you can apply the semblance for the other layers. And we also can use this kind of method to considering another situation, because the less than 10 years ago, the drilling operations were much more complex, because they used to apply different kind of drill bits and structures for different kinds of geology. You couldn't perform drilling with in a carbonate or in a salt with the same bit. Nowadays, there are equipments that are able to deal with different kinds of geologies. So for this reason, you don't have to be so accurate concerning the layers above the target reflection. So you must know what there is above the target reflection, but you don't need to be so accurate. So just performing this analysis to calibrate the semblance, and then you can perform a generic analysis for the other layers. That's the second scenario.
Okay. Let's see. On page 82, about the PVO analysis, you mentioned that you tested the method for SV reflection events with different critical angles. Is it correct?
I tested for what? I didn't.
For the SV reflection events.
It was tested for SV and incident SV and reflected SV.
Yes. And why you did this if you are dealing with OBN acquisition? I didn't.
Oh, this one was tested to be applied in near surface, because once we have in the 5 first models, we cannot find a phase shift, because the critical angle is much farther than we could obtain. So it couldn't be applied a method to find the critical angle in a model that we could reach the critical angle. So that's why I tested these 3 models to reach the critical angle and then apply the PVO analysis.
Okay. Now it's on page 185 about the residual travel time curve analysis. You present a lot of graphs of the residual errors for different the different geologic models you test, and consider the different approximations along the entire offset range. And you observed and you show this these errors vary according to the offset. But you mentioned on this page that an approximation that shows a very good fitting all along the curve, but not a good fitting closer to the time for 0 offset, is not considered a good fitting. Once the value of this parameter would be recovered with a higher error. I didn't understand very well this statement. If you want of the main product of the seismic reflection processing is the stack section, so the best would not be the best fitting for all along the offsets. I didn't understand exactly to analyze just the near offsets, considering that for the stacking, you analyze all the range of offsets.
Yeah, I analyzed all the range of the offsets just to try to understand which equation could perform this curve fitting, even for this kind of conditions. I strong with a high difficulty to analyze. It was just to it wasn't to be it doesn't it must not be applied this way. It's just to test how the equations work and where are the limits of them.
Oh, okay. And finally, in conclusion, you mentioned that one of the good products of the approach for the automatic peaking technique that you employed is the possibility to get information regarding the phase variation in order to get better results for NMO correction. But you, in my opinion, you barely demonstrate this statement in your thesis. And if I understood correctly, only for SV event, not for the converted waves. Why you include this as a conclusion? I don't know. I'm not sure if it's a conclusion of your development in your thesis.
Which paragraph, please?
It's just a moment. In the conclusion, it's a moment. I'm not there. Okay.
Hello, Nelson.
Wait.
For here.
Wait.
Could you give response to Professor Renata, please?
So, yes. Oh, yes. You're not hearing me?
Sorry.
You are hearing me?
Yeah. No. Yeah.
I don't know. Oh, okay. Yes. I'm looking for. Yeah. Yes, it's the first paragraph. Let's see. The first paragraph, Nelson, the conclusion on page 2.
I found it.
And I was asking if not. No. Sorry. It's not this one. Let's see. No. Sorry. It's not the first one. It's another question. I'm just. Well, I'm not finding, but I try to repeat. You mentioned about that a good product of the approach of the automatic peaking technique that you employed is the possibility to get information regarding the phase variation in order to get better results for NMO correction. But you barely demonstrate this statement in your thesis, in my opinion. And when you show some results, it was for SV event, not for PSV event. And why you include this as a conclusion of your study?
Well, because this study helped me to develop the automated peaking, because they use the same mathematical proposition that about the phase proposed by Tommaso in 2010. So it's It's practically the same application to calculate a trace, the spectra in a trace, in a seismic trace. But the PVO analysis, I check the global minima, and for the automated peak, I just compare the spectrum among them. So the algorithm is almost the same. I just extract different informations. So that's why I put this in the test.
Okay. Thank you, Nelson. I don't have further questions. Congratulations for your work. Congratulations, Professor Priimenko. And I finish here. Thank you.
Thank you very much.
Okay. Thank you very much, Professor Renato, for your questions and comments. And now we have almost 2 hours. It's means it's only on the limits of our work today. By this reason, I will not speak a lot because, in fact, I spoke a lot with Nelson during all this time, final years, when he prepared the almost final version of his work for today. Okay, now, first of all, I would like to say many things to the members of committee, because I know it was very difficult to participate through the internet because of our internet connection, and very big difference. One of them, Professor Mitrofanov, lives in Russia, and Professor Ranajit in Poland, and we, Professor George, Renato, and me in Brazil. And it was a real international committee, represented by people who represent different geophysical schools, from Russia, from Holland, and from Brazil. And now I would like to invite the member of committee for secret, how can I say, secret office for deliberation, for discussion of the results of final results of our meeting today. Well, yeah, please. Okay. Mm-hmm.
Ok, Richard, agora eu fui para o seu escritório. Beleza, vou só desligar o microfone então. Richard? Tem tempo para eles avaliarem ou não? Tipo... Ah, tá. Depende do que. Entendi. Oi. Estão falando para onde eles vão nas férias. Entendi. Ah, beleza. Ele tem que entrar aqui, né? Ah, entendi. Ah, beleza, então. Valeu. Obrigado. Richard? Tudo certo? É só saber se, se eles ainda estavam. Beleza. Tem alguma novidade, Richard? Será que não caiu a conexão de algum deles? Ah, tá. Dá para saber quem que está assistindo? Agora que eu abri a live no YouTube. Ah, beleza. Professor, seu microfone está desligado.
Sorry. Agora, ok. Quem está faltando? O Mitrofanov?
E o Ranajit.
Tá bom, tá.
Pode ser que eles tenham saído mesmo, não retornado. Não. Eu acredito, Richard, que eles não entenderam, a gente ficou... mas, assim, eu não sei, o professor Schlaich está aqui presente, o que nós conversamos lá, eu acho que a gente, não sei se é permitido, acredito que sim, a gente finalizar, estamos em três aqui, conversar e passar para o
Seja, inclusive, o principal mesmo da transmissão, a CPG, é a arguição. Priimenko está tendo um eco.
Eco?
Priimenko, quer dizer, isso.
Acho que só falta o Ranajit agora, Richard.
Mas eu acho que o professor Priimenko pode começar, não?
Posso começar?
Eu acho que não há necessidade de estar aqui presente nesse momento, acho eu.
Okay. Can I start? Renato?
Yes, you can start.
Okay. I would like to speak about the decision of our committee today. So, the principal results of decision of our committee today about defense, the result is approved, ou aprovado. Tá certo?
Thank you.
Tá aprovado, it's approved, but with condition, it's that after that you have to, by my supervision, you have to incorporate in final version of your thesis all suggestions, comments, and correction which were done by members of our committee. And
So, Nelson, sorry, Professor Priimenko, can I put in the chat the comments, the observation that the committee
please,
is doing, okay? And that Nelson, you have to follow this, okay? I include here.
Okay.
This will be record in the document, in the ATA. So you have to attend this condition.
Okay.
And hello?
Professor Priimenko, okay.
Nelson, did you see the text which
Yeah, I just read
was
it.
elaborated? Yes. So, how can say that as a result of our defense today, that the result, final result, that the thesis was approved in these conditions, that you need to put in the final version of your thesis the observation, comments, and correction which were done by members of our committee.
Okay.
Professor Renato, is it correct?
Yes, and I have just received the answer from the graduate secretary informing us that the time is 60 days starting from the defense day. So you have Nelson's 60 days, 60, to attend this orientation. Okay.
Yeah. Okay.
So congratulations from my part. You have a lot of work to do, so
Yeah.
work hard.
Okay, thank you.
Yeah. Of course, you will have a lot of work, but it is necessary to do. Yeah. Congratulations.
Thank you very much.
Yeah.
Nelson, sorry, Professor Mitrofanov, just let me say it em português to you. Você foi aprovado, parabéns, mas veja que eu não sei exatamente como é isso na USP, na Unicamp, essa coisa é aprovado condicionalmente, não é um aprovado completo. Você realmente vai precisar fazer essas modificações, senão a condição de aprovado troca a posteriori ainda para reprovado, tá? Então tem um certo perigo nisso, e 60 dias é curto. Você vai ter que se dedicar bastante. Então, eu só queria te dar esse alerta.
Okay.
Obrigado, Yuri.
Nelson, and I think that you will look on all comments and check all points which given for you as Georgian, because he, I don't know how to say, prepared for you good example on the future at that time, how you need to work with the text, okay? Try to study, and maybe you will teach in future students on your example.
Okay, thank you.
Good luck.
Thank you. Well, at first, thank you very much for my advisor. Thank you, Professor Priimenko. I'd like to thank also my co-advisor, Professor Fernando Ribeiro, my supervisor during my period in the Netherlands, Professor Dejan Draganov. Thank you to all the members of the committee. Thank you, Professor Schleicher, for all the comments, for the corrections. Thank you, Professor Renato. Muito obrigado. Não só por hoje, mas por ter avaliado os meus relatórios ao longo da minha tese. Thank you, Professor Ranajit, for all the comments also, and for all the help when I was in the Netherlands. Thank you, Professor Mitrofanov, for your comments, for questions. Thank you very much. Thank you, Richard. Valeu, Richard, por fazer tudo isso aqui dar certo também, né? Só hoje, mas ter ajeitado as coisas para todo mundo, para mim, uns dias atrás, e para os professores também. Bom, agradecer também aos professores, não só os que me orientaram, os que foram da banca, mas os outros professores que fizeram parte de todo esse desenvolvimento, tanto durante o doutorado como no mestrado e durante a graduação e até antes disso. E obrigado pela minha família e pelos meus amigos de terem me assistido aí, aguentado essas 5 horas aí. Valeu pela paciência de todo mundo e obrigado por todos vocês de terem lido a minha tese. Eu sei que quase 300 páginas é bastante coisa, então eu sei que vocês são muito ocupados então obrigado mesmo para vocês 5. Thank you all from the committee for reading almost 300 pages, so thank you very much.